only on the controller, this automating, but soon we will have also the orchestration. So the orchestration is how to choose the virtual machine, how to link this virtual machine, and how to urbanize this virtual machine on the data centers. And another thing that is arriving also is the self-driving systems with a lot of artificial intelligence. So this is the panorama of the data centers. We have the central data center with a cloud, and we have three possibilities on the edge. So the MEC is mobile edge computing, is just behind the antenna, the 5G antenna. We have the fog. So the fog, it's from 2013 from Cisco. They proposed this fog to connect things. And more, we have what we can call the skin, mist, or sometimes femto data centers is really on the edge. So it's very close from the user. The user can be connected directly on the skin data centers. So we're more and more working with these 4 layers. Another important thing in this new generation is Sdn Network, obviously. So the Sdn, just to recall what is this Sdn technology, is the fact that you have a controller, a central controller, and when a user is trying to enter the network, he sends a first packet, and these first packets go indirectly using a signaling system to the controller, and the controller will decide of all the things. So we'll decide of the path, sending messages to add a line in the table, in the flow table, and then you can open your path in the network. So all is taking into charge in the controller. So if I summarize where we're going in the fixed internet, it's obviously virtualization, then orchestration, so automating, and then we will have the cloud native, so using container, and this is the decomposition of services into microservices. So this is the way we will have in the next year in networking. Now, if I'm looking at the telecom operator, where they are, and we're working today on the 6G, and there is some labs with more than 100 people working on. So we have a generation every 10 years approximately. So the 6G should arrive in 2030 approximately. So I will have some slide about that, about this 6G. But first, what is the revolution into for the 5G network? We have 3 parts in the mobile network. The first one is how to link the user to the antenna. So this is the radio part. And this is not at all a revolution in 5G. It's just an evolution of 4G. Okay, the capacity is increasing a little bit, but it's nothing. So there is nothing new about that. The revolution for the 5G is in the RAN and in the core network. In the RAN, so in the radio access network, and in the core, we have in between the data centers, and these data centers are MEC data centers. So it's mobile edge computing. And why this is a revolution? Because all will be virtualized in the 5G into these data centers. So for example, the antenna would be in parts virtualized into the data centers. So it's why, for example, it's so complicated to compare the resource, because some resources were on the antenna before. It was the node B, and in the 5G, the node B disappeared, and it's totally virtualized into the data center. Why the capacity is increasing a lot in 5G? It's because we are using, first of all, a new band. It's between 3.2 and 3.6 gigahertz, and opening new bands over the 20 gigahertz. So it's millimeters wave. And we have a lot of space because in this slide, you can see that between 20 and 120 gigahertz, we have approximately 100 gigahertz. And currently the spectrum, the total spectrum is just 20 gigahertz. So it's 5 times more. And it's why the traffic could increase a lot. And if we're looking at the research for 6G, we are working over the 120 gigahertz, going to the 1 terahertz. So we'll have more and more spectrum for this new generation. Just recall where we are in the 5G, because we talk a lot about 5G, but in fact, 5G is not finished at all. We have 3 phases in 5G. The first one was the release 15 and in June 2018. And this first phase, we defined only the radio part. So what we named the NR, the new radio. So we're using the 4G technology for the RAN and the core network. It's what we named the non-standalone mode. And when today we're talking about 5G, we're talking only on this part of the communication between the smartphone and the antenna, but not at all about the RAN and the core network. It's why it's very confusing. And this is only the part when we talk about new 5G networks, and when we talk about millions of people using 5G network in China, for example, is just the connection of the smartphone and the antenna. And then after you're using the 4G technology. It's why the increase in traffic is totally negligible today. And it's true now that the capacity of the antenna is increasing. But as a fact, we're using 4G RAN and 4G core network. What we can gain with on the radio part is lost into the network. Now the important release is was in June this year, in 2020, and in this release we defined the RAN and the core network. And what is important in this normalization is the slicing technology and the cloud RAN. So we will have in the future full virtualization using Nfb architecture, so network function virtualization. We have also millimeter wave, and the capacity should increase by a factor of 2, going from 10 to 20 gigabits per second. One of the most important phases of the 5G will be in October 2021. So it's why we're in the middle of 5G definition. What we have in this release 17, it's NR light, for example, so a new radio light. It's for connection of the car, but not for the control, but for the user. So we can have a high throughput, but with the light technology instead to have all the 5G technology. We will have also a new radio above 52.6 gigahertz. We will have also improvement replacing all SIM and eSIM by iSIM. So I will talk a little bit about that at the end of my talk. A very important thing also is the new radio broadcast, because we should remove all the TV network. So TV network will be replaced by 5G and then 6G new radio. So we could recover the bandwidth used by this TV environment, and this could be very nice for 5G and then 6G. We will have improvement of the coverage with a mesh network. There are all the definition of the application, and mainly about Industry 4.0, so the automation of the production. We will have also the normalization of the new radio non-terrestrial network. So it's for satellite. So it's why all the satellite constellation we have today are not compatible with 5G. And this could be a problem because it's a constellation for objects. And this could be really a problem because it could be proprietary technology used to connect the objects and the things. An important thing also will be the NRU and license, because 5G would like to be implemented on the unlicensed band, like the Wi-Fi. So it's possible that we will have a competition between the 5G NRU and the Wi-Fi. But I will be comment on that because it's really very, very important to have this competition between Wi-Fi and the 5G. And a lot of things about power saving also in this release. Now we are thinking about the first elements for the 6G in 2025. So it should be the release 18. And again, there are some revolution because it's the end of cellular networks. And cellular networks are replaced by ultra-directional signal. So 1 BM per user. So we are going from antennas with 1,024 antennas, sub-antennas, and then 6G, we will have 1 million antennas just on the board. So it's possible to have 1 antenna per user. Another problem on what we're working today, it's the scalability of the slicing technology, so virtual networks. We should have also totally self-driving systems, and the security will be based on iSIM, integrated SIM. So just a word about the antenna. So the antenna we will have in the 5G with 1,024 sub-antennas. In the 6G, we will have 1 million sub-antennas. So the cell, in fact, there is a cell, but it's few centimeters square centimeters. So it's just one user. So it's why there is no CSMA or CDMA and so on. It's not necessary because we have direct communication between the antenna and just one user. Now, if we're looking at the RAN, it's where we have the revolution in 5G. And so in this revolution, we have these data centers, these MEC data centers, mobile edge computing, and all the G not B will be virtualized into these data centers. So the idea of 5G is to remove all the machine between the user and the data centers. We will have just one antenna because we cannot virtualize the antenna, but the antenna is just taking the signal arriving from the smartphone and sending this signal to the data centers. The antenna is doing nothing else. All is done by the data center. And we will have a lot of applications. So it could be also a good opportunity for operator to enter in competition with the Google and Amazon and so on, because we will have a data center before the central data center, so they can stop the flows into their data centers. But the problem maybe is that they don't have the people to do that. That could be a problem for the operator. Now for 6G, and in the RAN, the data center will be integrated directly in the antenna. So we will have still a smaller and smaller data center and totally integrated into the antenna itself. And if we're looking at the vision of Google for this 6G, because they would like to enter this environment, where is the antenna? The antenna is in the mobile of the user, or just very close from the user on his desk, for example. And all these antenna will be linked together. So it's a mesh networks of antennas. So they would like to have this new kind of networks that we call sometimes the Uberization of telecommunication, because all the network is with the user and no longer with an operator. So now if we're looking at the slicing, what happens with the new generation? In 5G, we will have a lot of slice, but the three main slices will be for Internet of Things, will be for vehicles, and for high throughput, high capacity, and mobile high capacity. But this number of slices should increase, so we will have horizontal slices, and the horizontal slices corresponds to an application, and we will have vertical slices, and the vertical slice will be for the enterprise, for the companies. One company will have vertical slice, and inside this vertical slice, we will have horizontal slice. So CJ will have this technology as ultra slice network, so one slice per user, and one vertical slice per company, but this vertical slice will be composed of a lot of horizontal slice if necessary. So on the figure, we have different companies, one company per vertical slice, but inside, sorry, hold on, what happens? I cannot go back. Yes, okay, working. So inside the vertical slice, you have the horizontal slice of the different services into the company. Now, if we are looking at the automation, we try to do that in 5G, and we have some software like ONAP, Open Network Automation Platform, and to try to automate the network, but it's generally mainly for the controller, just arriving for the orchestration and for the management. But we have to wait, in fact, for the 6G to have a totally automatic systems with a piloting system. But there are different vision, and say three visions. The first one is a strongly centralized network. It's, for example, Huawei is doing that, working on that. We have a system using digital twin, and Japan, Docomo, for example, is working on that. And Google is working on the strongly decentralized, so it's totally opposite from the Huawei proposal. So just a slide on these three possibilities. The first one is, say, it's a slide from Huawei. It's huge data centers with billions of servers, centralized, and totally smart data centers. And then they are connecting clusters of antennas, so they can connect a large number of antennas. And so all is centralized. The proposal of Docomo in Japan is to use what we name a digital twin. So it's something like a virtual machine doing exactly the same thing as the physical space. So all what happens in the physical space has to be sent to the cyberspace with the digital twin, and the cyberspace is deciding of all the things again, but it's not said that if it's centralized or distributed with Docomo. They just say it's a digital twin. So it could be a distributed digital twin or centralized digital twin. It's not indicated in their paper. And then when the cyberspace decide, then after you go back to the physical space. And the last one, as I said, is Google and the proposal for the 6G of Google. So we can see this environment coming soon through the Google Mesh and Google Home, that's well known today. And they join the two environments into the Google Nest. And then it's announced the Google Mistral. And the Google Mistral is FM2 data centers. It's a data center. They will have 1 terabyte of memory. They will have 10 or 20 processor with 10 cores. And these small data center will be connected using Wi-Fi. So Wi-Fi also, it's another possibility, but could be also device-to-device technology, 5G device-to-device technology, but all this FM2 data center will be connected and form the network. It's why, again, we say uberization of telecommunication. Sorry. Going back to the mobile internet. What is the mobile internet? I said it's all mobile antennas. So it's MANET, VANET, or FANET. So it's a mobile ad hoc network. It could be a vehicular ad hoc network, or it could be flying ad hoc networks. Okay. And what kind of technology we have for that? But we have a very, very low, not very fair technology. It's 802.11p for vehicles. But it's very slow technology and not working very well. They just introduced priorities to be sure that for control, the packet will arrive quite soon to the destination. But we have really to extend this generation, and we're working on the 802.11bd, and this is very important, because this technology will use the Wi-Fi 6, 6E, and 7, and the endeavor could be at 300 kilometers per hour, almost like 5G. So it's really a new generation of Wi-Fi, and it's mobile Wi-Fi. So the idea is to take the Wi-Fi 6 or 6E and to have this in mobility. So, for example, this Wi-Fi 6 is into vehicles or in train or something like this. And what is interesting in this Wi-Fi 6, you can see that the main features is OFDMA. So before the CDMA-CE, you have an OFDMA, so you can you can share the bandwidth much better than in the previous Wi-Fi. We are using also beamforming. So we have 8 spatial streams. So it's why the total capacity is high, because we have to add these 8 different surface spatial streams. The channel bandwidth could have 160, and with an hertz we have 10 bits. And the 6E is just the extension on the new available band, the spectrum at 6 gigahertz that is going to be free soon. It's almost free in the United States. It's almost free in Europe. And this band is really important because we will have 1,020 megahertz free. So you can enter the spectrum very easily, and we have a very high throughput using the spectrum. And if we're looking at the Wi-Fi 7 arriving on the market in 2 years approximately, so the capacity is very high because now we have a 16 stream. The channel could go up to 320 megahertz. So it's why the 6 gigahertz spectrum is very necessary for that. An important thing is the operation is full duplex. Spectral efficiency is 12 bits per hertz. And there is the decoupling of the data plane and the control plane. So the Wi-Fi 7 is looking more and more to the 5G. So I will come back on that, but Wi-Fi and 5G is now converging to the same technology. So I will come back on that because this could be an important thing for the future. And yes, this Wi-Fi and 5G is converging. And this is a slide coming from Qualcomm where they're working on this convergence. So the Wi-Fi could become a 6G access point, so totally compatible with 6G. So that's important things. Now, for the years arriving, I think that the technology that could be used is a multifier. Multifier is a technology using in the same time 5G and Wi-Fi. And this technology is as follows. We first, if we have available channels, and for example, we have some channel with Wi-Fi and trying to send messages using 5G, I'm looking at the available channel, and if one channel is available, I can send my messages, my packets using the 5G. If there is no available channel, in that case, we are using listen before talk, LBT technology. It's a new it's not really a new technology because we are using this in Wi-Fi, but it's a little bit different because in the back of, instead to have a fixed block, we have random. We have not fixed block, but the back of is after random, totally random technology. And so you are listening. If there is, for example, a Wi-Fi using the band, and the band is free, you can send using 5G. So in the same time, on the same band, you may have Wi-Fi and 5G. So it's an integration of Wi-Fi, but not total integration. So we think that in, say, 8 years from now, we will have a total integration of Wi-Fi and 5G. So at this Edge network, we have this kind of networks, and again, it's uberization. It's the view of Google, where all machines are linked using either Wi-Fi or eventually the 5G device-to-device technology. Could be any kind of technology between two devices. We can interconnect the clusters using 5G network infrastructure. That's possible. So to have very, very, very large networks. And currently, we're working on a project with Valeo. Valeo it's a French company, a big one, and they're working on wipers, and they would like to interconnect all the wipers in the world. So Valeo currently have the third approximately of all the wipers in the world. And so it's 2 billion of wipers, and they are thinking to add in the wiper a small femto data centers that we can name also skin data centers, and then linked all these small data centers by either 5G device to device or Wi-Fi, new generation of Wi-Fi, or eventually by using satellites. And that's the way, and we will have global networks, and all the cars will be interconnected, and people outside the car also could be connected on the femto data center. So it's a new network, and it's a totally mobile internet, taking part of this mobile internet. Okay, so we can do that also with drones at the edge. Link all the drones. Okay. So we can link the drones and cars, obviously. Another important thing is about satellite constellation. Why? It's we have so many constellations arriving in the market, and the first one is Starlink from Elon Musk. Should have 40,000 satellites by 2028. And they pretend to have 5% of the internet, of the future internet, and using this part of the mobile internet. But 5% of the total of the internet with these 40,000 satellites. Just remember that in the sky, there in the north, not in the south, but in the north, there is only 8,000 stars. So we will have in the total in 2030 something like 100,000 stars. So that also is a problem. We will have also the OneWeb with Airbus. Jeff Bezos decided also to go with a constellation with Kuiper systems, but they're thinking maybe to be a 5G technology. So using the narrowband IoT, for example, technology to link all the things in the world. So they have to wait because normalization will be in the phase 3 of 5G. So this Kuiper system, this constellation will arrive on the market in 2025 only. We have also Omnispace, and Facebook and Apple will be in this constellation. So as you can see, why all the people with that have billions are going in that direction is it's the cost. The cost is only $10 billion only. But this guy, Jeff Bezos and Elon Musk, they have this in their pocket. And what they expect as an annual revenue is between 10 billions and 30 billions. And just if we are looking at 100 billions objects to be connected at $1 monthly subscription, this represents 1,200 billions of dollars a year. So it's why they are going to this constellation. Okay, so just for the end, I have still 2 minutes, 3 minutes. The mobile internet is mainly these smart vehicles. So we will have 8 billion connected cars by 2030. And the driver will no longer drive. They will be connected on the internet. And this throughput is enormous because all this person span say 2 hours on the average, sometimes 3 hours in their car during a day. And they will be connected on the internet. And the future internet will be, half the internet will be the connection of cars. So as you know, we have a competition between Wi-Fi and 5G to connect these cars. First of all, it was Wi-Fi, then 5G is arriving, and now Wi-Fi is coming back with the BED technology. So we'll see in the future what happens. But if Wi-Fi and 5G is converging, in fact, it will be the same networks at the end. So I have a slide to recall that 5G is very interested into the connection of cars, and they're working on that. And Release 16 have the NR V2X technology, and will be finalized in the next release in 2 years from now. And so this is the future where all will be connected with small data center on the extremity, with also large data center in the center, because the full possibilities of data center will coexist. We will still need some central data centers, but we can go more and more to the edge and to these very small data centers. And if we're looking at Google, they would like to integrate in, say, 6, 7, 8 years from now, the data center into your smartphone. But this depends if they really have a market on the smartphone or not. If they don't have the market, they will prefer to have this small data, this edge data center, this sky data centers on your desk in your office. Okay, just a word about security. Quantum networks will be the way on long distance, for example. But I'm interested here in this slide on the iSIM technology. So iSIM, what it is, it's a SIM card, but integrated into the SoC. So directly with the processor. So for the Internet of Things, it's very, very important, because as soon as there is a processor, you will have a SIM card. But not only one, it's possible to have 2, 3, 1,000 SIM cards, because the SIM card is just a dust. It's nothing. And this is directly with the processor. So this is a way we will secure the future networks, and it's using the iSIM. So this will arrive quite soon now on the market. Okay, this is my talk. I hope that you have some more information about the future, and I'm ready to answer your questions.
Thank you very much, Guy, for your very nice presentation. Let's open to questions. Someone has questions right now? So if nobody has questions right now,
I have a question. Nice talk, Guy. Thank you.
Yes?
When you talk about the bin and you talk one bin per person,
Yes.
when the person move, the bin move with the person, or we have to change the bin? The bin is fixed or the bin move?
Yeah, the bin move. So the bin can follow the person. And this is important because, for example, for energy consumption, if there is nobody, all the bins will be stopped. If you have 5G or 4G, when you have an antenna still open, but in the future, as soon as in the night, for example, you will have just some bins, but they are moving, so they follow the user.
Okay, this technology is already good.
No, it's not at all available today. It needs at least 5 years.
Okay, thank you.
To have this, because in the 5G you will have directive antenna, but it's fixed. In the 6G, this will be mobile.
Thank
but
you.
In 5G technology, it's fixed, and it's more than 1,000 fixed antennas per board. So you can add more boards, and you have several times 1,000 antennas.
Thank you.
Thank you, Otto. Thank you, Guy. Guy, we have some questions on YouTube chat.
Yeah.
Two of them are from Célio Albuquerque, professor at UFF, and he says, "Thanks for the nice talk. Regarding 6G, is the 6 gigahertz band already available in Europe?"
This 6G, no, it's not available today, but very soon should be available. And it was decided for all the world. It's not only for Europe and United States. They're in advance in the United States, but in Europe should arrive soon.
Okay, thank you for your answer. And the next question is, 802.11ax client device will be able to operate at the new 6 gigahertz band, or will they need a new radio to use this band?
Sorry, I don't understand. Sorry.
In fact, he's asking if the clients of 802.11ax clients will need a new radio to operate on 6 gigahertz band.
Yes, absolutely. The AX, so the Wi-Fi 6, will use as soon as possible this new band. So it's why the name is a little bit different. It's a 6E. It's not. It's a new Wi-Fi access point because yes, you have to add this new band on the Wi-Fi. So you cannot use your AX technology today. You have to buy another access point.
Okay, got it. Thank you, Guy. And someone has some more questions? Not in YouTube. So, Guy, I still have some questions about the 6G cellular network. Some time ago, I was in a presentation that the keynote said that the 6G will be the joint of machine learning and blockchain on the cellular network. And I thought that it was kind of limiting that it's blockchain and machine learning. What do you think about it, about the use of these new technologies on the cellular network as the name of 6G?
Yes, I think that machine learning and blockchain will be useful for this 6G. 6G, but it's part for me. The machine learning and the big data will be part of the automating system. Because really the 6G is a totally automatic system. So instead to have a room, say, for 100 people controlling, managing, and the network, we should decrease to 10. So remove 90% of the people, but they will be replaced by other people that are thinking about architecture. So it's not just for the students. It's not just to remove studies on the different hardware and software. It's just the fact that all will be totally automated. And there, obviously, intelligent artificial will be very useful. So we're thinking about mainly big data and machine learning. Now about the blockchain, for sure, blockchain will be useful for different things. For example, the IETF is working today on the domain name using the blockchain. So when you buy a domain, the domain is inside the blockchain. But all the application where we need some certification, where we need to have the time where something happened, and not only a crypto system, but also all kind of system will use blockchain, for sure, I agree. And if we are looking at the Google proposal for the 6G, where all is distributed, the blockchain is a good solution. If it's totally centralized, okay, maybe the blockchain will not the best solution, but if already 6G is totally distributed, blockchain is perfect for that. So I agree that blockchain and technology, other technology in the artificial intelligence, it's okay for me for the 6G.
Thank you very much. And just another small question. You see the 6G as a totally distributed network for the controlling and for the application that is running on the network. It's not going to be like our 4G network where we have some operators that are the owners of the network. You think that it's going to be a much more distributed, isn't it?
For me personally, yes. But it's not the case from Huawei, for example. They said that centralization is much better because it's not as expensive. It's easier to control. I agree that for security could be and disponibility could be a problem. But okay, for me, I think that the 6G will be totally distributed. Why we are centralized today? Because we don't know how to work with distributed intelligence. It's very difficult to have a driving system with distributed intelligence. But in 10 years from now, we will know how to do that. So personally, I'm working on the distribution. I think that's the good way.
Thank you very much.
I have a question, please. Okay?
Go there.
Okay. Guy, you said about 6 gigahertz band. You are talking that there will be a new band that will be free for everyone?
Absolutely. It will be a free band, like ISM band, like the other one. I like the 2.4 and the 5.15. It will be a new free band and very large because it's a little bit more than the 6 gigahertz band. It's because it's 1.2 gigahertz bandwidth. And this will be available in all the world soon. It depends the country, but all the countries in the world agree on that. And after, they have to remove the band inside the 6 gigahertz. And this could ask for sometimes, maybe some years in some countries. But this should arrive very quickly because now we still have equipment with the Wi-Fi 6E. You can get one if you want, but it's useful only as experimentation today.
Who has on this band before?
I don't know exactly.
Okay, thank you.
So for our last question, Marcelo Amorim has also a question.
Okay.
Yeah, yes, Guy, thank you for the talk. Very nice. You very quickly mentioned the in one of your slides the quantum computing stuff. So, in your opinion, how much should we care about quantum networking in the future?
Yeah, quantum networking is arriving slowly, very slowly. So it's why in 10 years should be okay, mainly for security reason, because as you know, when we send a qubit, if it's not if somebody can listen this qubit between the sender and the receiver know this immediately. So you know that somebody is listening to your line. So you can ask the people to send again, and you are sure if it's a qubit that there is no interception. So that's a very nice property that we will use in security in the future. But about the quantum network, yes, I think we should arrive at very high throughput and with some security, but for me, not before 5 years from now. So we have to wait. It's still time for research and maybe the first experimentation on small networks. Say.
Okay, makes sense. Thanks.
Thank you, Guy. Thank you, everyone. I would like to thank Guy for this presentation. And
Thank you.
We are going to have a break right now, and we'll come back at 9:15. Thank you very much.
Morning. Hi, everyone. Can you hear me? Sounds clear?
Yeah, it's okay.
Yes.
Okay.
Yes, we can hear you.
Without the headphone is better. So, my name is Igor. I'm professor here at Federal Fluminense University in Brazil. So let's start our first technical session. We have 3 papers in this technical session called Security on Cloud and Internet of Things. Marcelo Morin is my co-chair in this session. So the first paper is entitled Attackers Are Not Stealthy, Statistical Analysis of the Well-Known and Infamous KDD Network Security Data Set. And the paper will be presented by João Vitor Vale from Universidade Federal Fluminense, Brazil. So you have a video about 10 minutes long, or 20 minutes long for the presentation, and after that you have a few minutes to the audience ask questions to João. He's online after the presentation.
Hello, my name is João Vitor. I am from Federal Fluminense University. I am student in the Telecommunications Department, and I'll be presenting this work, which is called Attackers Are Not Stealthy, Statistical Analysis of the Well-Known and Famous KDD 99. This article was written in collaboration with Martin Androni Lopes and Diogo Ferrazani Matos. I would like to begin this presentation with a reflection. I suppose we've never been so dependent of a technology as we are of internet nowadays. From getting food to book a plane or chat to a colleague in the other side of the globe, internet has made itself an essential item so we can carry on with our most simple daily tasks. To illustrate this thought, I brought some numbers. As we can see, almost 60% of the worldwide population are active internet users. 52.5% are mobile users. 50.8% are active social media users. And the top countries in numbers of internet users are coincidentally the ones who have the biggest population: China, India, USA, Indonesia, and Brazil. Since the globe is more and more connected, there are some paths that this technology evolution can lead us. I would like to focus in the Internet of Things, since it's getting more and more space into innovation-based companies and has very interesting solutions are emerging. This technology would not have this boost if not by the development of other technologies. I'm talking about cloud computing and big data analytics. Those technologies enable to process and transfer of huge amounts of data that these IoT devices generates. As we can see, the evolution of IoT solutions are a big step, but the question is, can it keep up with the pace in security as it grows in the usage of data? Apparently not. But then, how can we increase the security for IoT devices? One possible way to do that is by implementing an intrusion detection system, which is basically a system which monitors and analyzes events in computer networks. Besides that, it's versatile and can be installed as a software or embedded directly into the hardware. They are divided in 3 classes: anomaly-based systems, which seeks for behavior that differ from normal pattern, signature-based systems, which focus in finding a non-attack pattern, and hybrid-based systems, which are basically the combination of an anomaly-based system and a signature-based system. Also, there are a variety of datasets which can be used to model novel detection systems. Two common use security datasets are the KDD99 and the NSL KDD. The KDD99 is derived from DARPA 98 dataset and was created for knowledge discovery in databases computation, which is a data mining competition. It features four classes of attacks: denial of service attack, which is an attack that aims to deplete some of the network resources and turn that unavailable to the users. User to root attack, which is an attempt to get root privileges as a regular user. Root to local attack, which is getting access to a network by controlling one of its users. And program attack, that is basically an attempt to get information about vulnerabilities of a network. The NSL KDD has the same features and attacks as the KDD99. It was created with purpose to correct the deficiencies in the KDD99 dataset, such as the removal of duplicity and balancing of attack and normal registers. By using these datasets to create IDSs, we noticed that they possess some drawbacks, which can affect the performance of the IDS. In our study, we identified some flaws in the structure of the data, such as the presence of imbalance between classes of attacks, redundant registers, high dependence between variables, and difference in distribution between attacks and normal traffic. And those flaws have some impact in the construction of the IDS. The effects are mostly related to the overfit of the models, poor performance when dealing with real-time data, and this causes the incapability to detect new attack patterns. In this work, we propose a method to identify the problems in the KDD invariant that's basically a statistical analysis that takes in consideration the correlation between the variables, the use of hypothesis tests to verify the relevance of the variables, a comparison between the distribution of attack and normal data, and modeling of continuous variables by using density probability function. This method also brings some benefits, such as the better understanding of the high bias cause, and enables the analyst to predict the effect given by variables with the same distribution. This is the flow that we used when dealing with the data during our analysis, mostly made of three stages: pre-processing, where the dataset will be first prepared and there is the cleaning of the dataset, the feature selection and training stage, where the data will receive the last steps of preparation before being used to train a machine learning model, and the final stage, when the machine learning model will be tested and we will evaluate their performance. Being more specific, the stage of data processing, we execute some very important steps such as the removal of attacks that are not DOS or probing. We also divide the in-sample set into the training set and validation set. We also make the separation of the out-of-sample set as a test set, and also run the codification and regularization steps of both in-sample and out-of-sample dataset. After the pre-processing stage, a very important step is the feature selection, which aims to calculate the relationship between the variables or calculations from machine learning models. The goals in running this step is to select the most relevant variables to prediction and also reduce the loss information and increase speed. The techniques we use to get the most important features were the recursive feature elimination, Anova F Test, and random forest importance, which is based in the reduce of genes impurity. After other important step before using the data as input to train the machine learning method is the balancing of the training set. To accomplish this, we accomplish this by using SMOTE, which is basically the insertion of synthetic registers without adding information, and works by the isolation of a region next to minority class observation and adds data that replicates this class along the region. A machine learning map concept is basically speaking, is the application of statistical concepts and mathematical optimization to extract analysis according to the input data. We used machine learning with the goal to use models with good performance dealing with categorical features. The algorithms that we used in this study were the decision tree, random forest, and logistic regression. To evaluate the performance of machine learning methods, we make use of some important metrics. Those metrics are the accuracy, which is the rate of correctly predicted results, precision, which is the proportion of positive predicted results, specificity, and recall, which are the capacity to predict a positive and negative result. F1 score, that represents a measure of a test accuracy. It is basically the harmonic mean between precision and recall. The ROC curve and the AUC. ROC curve plots the recall versus the sensibility, while the AUC represents the area under the ROC curve. The feature analysis is basically the statistical study of the variables of the dataset that was mentioned earlier. We analyzed the statistical properties of the dataset based in three different manners. In this study, we used the correlation heat map that checks the correlation between features and show the dependencies by color range. We also used the candle rank correlation coefficient that this analysis measures the relationship between features and the target variable, and we also used the Anova F Test. This test checks the significance between different groups, and it's useful to analyze the differences between samples. The higher the value of the test, of the score, the F value, the more relevant the feature is. The correlation heat map, which is shown in the figure, shows basically the correlation between the variables in a range from hot, which is close to 1, to cold, which is close to -1. As we can see, there are many hot and cold spots, meaning that many variables are correlated to each other. This graph shows the value of candle coefficient for each one of the continuous variables, showing that some of them have high dependence with the target variable. This table shows the Anova analysis for each one of the continuous variables in the dataset. Notice that the highlighted features have a high F value, which means that those variables possess high statistical importance to distinguish attacks. The study also allows, since we are analyzing more of the continuous variables, to approximate them by a probability density function. From the metrics obtained after testing the machine learning models, we observed that from all the models, the best results are from random forest model and recursive feature elimination selected method. Also, by analyzing the features, we can notice that most of the features are highly correlated to the target variable, which consolidates the bias into the models. And as we come to a conclusion that the difference implicates in the high performance from all the models. As we can see here, all of the models have high value of AUC. Random forest being the one with the best results for Anova test, given that it creates a cluster with the most statistical relevant features. This entire analysis brings us to some conclusions. We identified some statistical properties from the dataset which may cause bias to classification models. Some of them are related to the correlation between variables, the dependency of important variables with the target value, and the important features possess high capability to cause differences between attack and normal traffic. Possible root cause for this is the construction of the original DARPA 98. Advice: when analyzing real-time data, better consider all the data sets along with this KDD99 to enrich your machine learning models. The variables properties cause differences in the attack distribution and put them in evidence, revealing that attackers are not stealthy. This work grants us some opportunities of future works, like the application of the same methodologies to other security datasets. Also enables us to develop methods that mitigate existing flaws in KDD variant dataset. Also develop a safe, reliable, and scalable security dataset. Well, this presentation comes to the end. Thanks for the opportunity to present this work. I hope you guys enjoyed. Stay safe from COVID-19 and goodbye.
Thank you, João, for the presentation. You have time for questions. João, can you open your camera to answer the questions?
Hi, can you see me, Hugo?
Yeah.
Okay.
So, people in the audience, if you have questions, please indicate here in the chat. I'm not able to see your raised hands. So Marcelo has a question. Please, Marcelo.
Okay, very short one. So João, thanks for the talk. You mentioned at the very end that you intend to conduct similar experiments and analysis with other security data sets. Which ones do you have in mind? Because I'm not specialist, but I've heard from a few colleagues that these data sets are quite rare.
Yeah, that's a very good question because yes, the KGG is the most common data set, but there are also other institutions that provides data sets, internet security data sets. I don't have the address right here, but I was searching for another data set to another network data set, and I found some universities in the who provides internet security data sets. If I can find the link, maybe I can share. But now I don't know the exact number, the exact name of another data set, but I know that there are some institutions that Diogo gave a link. Well, there are other ways to search for security data sets, and it's also very interesting as to very interesting to research this data set and explore it too. I hope I
Sure. Thank you very much, and
okay.
thanks for the link.
Thanks.
More questions, please. João, I have two questions. The first one, concerning the results, did you have find a optimum number of features that you have to use to analyze the data set, or it depends on the algorithm?
Yeah, mostly I fixed the number of features to 15. I fixed to show to analyze the 15 most important features. But
Okay. But do you have in mind to evaluate for different values, or it's not a very important parameter? What do you think about that?
yeah, it's important to evaluate the number of features that must be considered when constructing the machine learning model.
Okay.
Diego,
Questions?
just a remark. In fact, in this work, it's not intended to find the optimal number of features, but in fact, we are trying to see the correlation between features and the output class. Thus, in this work, we were focused on seeing the relation and how the features influence on the on the output class, and that's
Okay.
interesting because we see that the features are high correlated with the class, and it's not what we expect for a stealth attack, and thus that's the problem that we say that the attackers are not stealth.
Okay. Thank you. More questions? I have a question here in the YouTube chat from Silvio. So, do you have observed some improvement considering the computational time reducing?
Sorry, can you repeat?
Do you have observed some improvement considering the computational time reducing? Let me try to. Diogo, can you cut and paste the question from the YouTube chat here to the WebEx chat? I'm
will
not
try
able to copy the message because I don't have a YouTube channel to use the chat.
Okay, just a
Well,
moment.
I
Yes.
think that the question is in the training. The timing has reduced or not?
Yes. That's yes, that's a very very good question. Yes, I made the training without making the feature selection, and afterwards I made the feature selection method and trained the machine learning models, and I noticed some reducing in time of computing time processing. But the data set itself, it's not so large. The data set I used is about
João, but I think, João, sorry, but I think the question is that you have constructed a new data set. It's right?
no. I did use an existing data set.
So, but you eliminate a lot of things. What
Yes.
probably the question is with the new data set that you have eliminate a lot of things if you have reduced the training time.
Yes, of course. Yes. The time is very reduced due to these features that I removed because the data set itself has about 41 features and I reduced it to 15. So it would make the processing much more fast.
Okay, one last question. I have one. I know it's not easy to answer this question, but do you have a feeling about the results that you will obtain in the new data set, or how much your results are dependent of the data set you have chosen?
Well, the whole point of the paper is it's not about the result, but the whole methodology of the analysis. So the point is not to focus on reach the same result. The point is make the analysis, and with this analysis we get the result that the data set the focus is on the statistical analysis of the data set. Seen by this perspective, there must be no difference in our analysis to a different data set. It's not we are not hoping that the results must be equal or have the same performance as we had in the KDD99.
Okay, John, thank you very much. Very interesting work. So let's move it to the next presenter.
Thank you.
Thank you very much. So the next paper is called TEMIA-NT, Threat Monitoring and Intelligent Data Analytics of Network Traffic, The authors are Lucas Guimarães, Gabriel Rebelo, Felipe Fernandes, Gustavo Camilo, Lucas Airan, Daniel dos Santos, Luiz de Oliveira, and Otto Carlos Bandeira Duarte from Federal University of Rio de Janeiro, Brazil. So Lucas Guimarães will be the presenter. So let's play the video, and after the video, we have time for questions.
Today I'm going to present the MNT, that is Threat Monitoring and Intelligent Data Analytics of Network Traffic. This work is made by me, Lucas Guimarães, and was co-authored by Gabriel Antônio, Felipe Fernandes, Gustavo Camilo, Lucas Airan, Daniel dos Santos e Luiz Gustavo, under the guidance of Professor Otto Carlos Duarte. So before introducing the system we developed, first I'd like to talk about current security issues. First, the security systems we have nowadays offer very low performance, in that they are inefficient in the detection of threats. According to a research done by Cybersecurity Ventures in this year, around a quarter of cyber attacks take from weeks to months until they are detected. This is mainly due to the need of human intervention, which makes the process of intrusion detection a slow one. This results in a high risk of irreparable damage, because the longer it takes for an attack to be detected, the longer the attacker can damage the organization. Furthermore, due to the current scenario of big data and Internet of Things, it becomes even harder to detect attacks. Big data, due to the increasing, to the high volume, volatility, and variety of data, it becomes harder to classify what is attack and what is normal traffic. And the Internet of Things device possesses low computational power, which makes it harder to detect attacks into the devices. So, there is a need for faster and more accurate detection systems. One way that we can implement such systems is through machine learning methods. That way we can remove the need, or at least reduce the need for human intervention in the process of threat detection. Also, you can use clusters, so we can operate these data, we can implement those methods so they can operate on big data. So to implement those techniques, we can use the Lambda architecture. The Lambda architecture is composed of 3 layers. The first, the stream processing layer, is responsible for receiving and processing data in real time. In the case of intrusion detection, this layer is responsible for receiving the traffic and classifying it as either attack or legitimate. The second layer, the batch processing layer, is responsible for processing datasets so that classification models can be created, and these classification models will be used on the stream processing layer. These are going to be, the dataset is going to be stored through a distributed file system, because we are going to operate on clusters, as said previously. And the last is the service layer, which can show to the network administrator information regarding the real-time classification that is being done by the stream processing layer, as well as a historical visualization of the processing done on the batch processing layer. So, the idea is to implement a virtual network function, VNF, to provide precise and scalable real-time threat detection. So, to implement your proposal, I change us to use the Pushback platform, which is a unified analytics engine for big data processing. One main advantage of this, compared to other big data processing tools, is that the processing is done whenever possible in memory, which offers a great advantage in processing speed, which you're going to need as we're going to be dealing with big data and high volumes of data in general. Furthermore, the Apache platform possesses multiple modules that can be used to take advantage of during a project. For example, it provides multiple classifiers and statistics methods to the machine learning library, the MLlib. The classifiers include, for example, decision tree, random forest, logistic regression. And the statistics methods include, for example, accuracy, FN score, AUC. So we can verify which classification models offers the best results for for a system. Furthermore, there's another model called the structured streaming, which is an engine developed to allow stream processing in a scalable and fault-tolerant manner, which is going to be useful in a system because, once again, we are going to realize the classification in real time. So to test closed system, we use the dataset made from real traffic from a telecommunication operator. The traffic was then abstracted into flows using the floatback tool. Those flows are abstracted using the 5-tuple, which means that they are collected using the source IP, destination IP, source port, destination port, and the protocol. And the tools also extract 40 features so that can help during the model creation. Furthermore, since we are using supervised classification machine learning algorithms, which require the use of labeled datasets, we use an intrusion detection system, which was Suricata, to classify those flows previously. The flow dataset contains 3.7 million flows and was balanced to avoid bias during model creation. So regarding the proposed architecture of the TMIA NT system, we have the system processes 3 modules and 2 modes of operation. The modes of operation are online and offline. The first of the modules is the data collection module. The data collection module is responsible for dealing with the data. This data is going to be used in the following modules of the system. In the online mode, the data is collected through sensor and traffic analysis and through other possible data sources, such as, for example, honeypots. The data is then passed to a data buffer, where it's stored until it is needed on the following modules by the system. On the offline mode, the data sets are stored in a distributed database. We use the Hadoop distributed file system. And these data sets are the ones that are going to be used for in the next module for the model creation. So the second module is the processing module, which also processes the online and offline modes of operation. First, the offline mode of operation, the training module uses the datasets in the offline data collection module to train the classification models that are going to be used during the online classification process. Those models are verified through the offline classification module, where it can obtain various metrics such as accuracy, FN score, so that the network administrator can verify which algorithms offers the best results for the data they have. In the online classification module, the data is passed through the data buffer to the classification models, which will then classify the data as either legitimate or malicious. Then the data is sent to a data enrichment module, which verifies the geolocalization of the source IP, which is going to be passed through the source IP, and then the data is passed to the next module. The next module and the last one is the visualization module, which simply receives and stores the data obtained from the processing module and shows the information obtained to the network administrator through a dashboard. In this dashboard, the user can see either the online data results, which means they can verify the amount of flows they're receiving each instant, and the amount of flows are classified as either attack or legitimate, among other informations. And there's also the offline process data visualization, which is where the user can see results regarding the classification model creation, which can see which algorithms are used in the training module and their respective results. Before entering the performance analysis we made of the system, first I need to briefly talk about the Apache Spark APIs. Apache Spark provides 2 main APIs, which are the RDG and the Data Frame Dataset API. The RDG was first introduced on Spark 1.0 and it means resilient and distributed dataset.
It is distributed because it is meant to work on a cluster. That means the data needs to be present in all the cluster nodes. And most important, it is resilient because the data is immutable. What it means? It means that you don't the data stored as RGGs is not changed directly. You must make operations and transformations upon the data. This means that as the data does not change and is only transformed, it can be easily recovered if a node fails. The following API introduced was the data frame dataset API. They work similarly, the only difference being that the data frame is an untyped API, dataset is a typed API. They were both introduced on Spark 2.0, and the main difference between this and the RGG is that they are structured, similarly to data in a relational database. As such, it allowed the introduction of several performance optimizations, which means that if you're dealing with structured data, it is incredibly beneficial to use data frame dataset instead of the old RGG API. So to analyze the impact of the API on results, we compare the model training time of a decision tree classification model using both RGG and data frame. For RGG, we used previous work of the GTA laboratory that implements the model creation of a decision tree using the RGG API. And for comparison with the data frame, use the mini tree, which uses the newer version. So, as can be seen in this image, the data frame completes the model significantly faster than its RGG counterpart, being 10 times more faster than the RGG. So for the performance analysis, we chose the following evaluation metrics. The first being accuracy, which is the total number of correct classifications overall, meaning the number of true positives and true negatives overall, over true positives, false negatives, true negatives, and false positives. The next was precision, which is the number of true positives over all the classifications made, all the positive predictions, meaning all the true positives and all the false positives. The next being recall, which is the total number of true positives over all the truly positive elements, meaning true positive over the true positive plus the false negatives. And lastly, we use the F1 score, which is the harmonic average between precision and recall. Our main classification metric was the F1 score, which we use because it considers both the number of false negatives and false positives, instead of considering only the true correct classifications as used in accuracy. So from the results, we can verify that the best results were the tree-based algorithms, in this case the random forest, the gradient boosted tree, and the decision tree, with the other algorithms offering worse results. Next, we realized that performance analysis of the flow processing rate. We chose to analyze the three best algorithms that we saw on the last slide, which means that we chose the three best ones. Because they offered highest accuracy and F1 score, I said. We then verified how many flows they could classify per second, simulating an online classification using the structured streaming module. We then could verify that the decision tree and the gradient boosted tree offer a very high classification speed. We estimated the amount of flows in gigabytes per second using the average flow size, and both process classification higher than 44 gigabytes per second. And the random forest offers a lower processing speed than the other two algorithms because of the way the classification model works. The classification model works. Different from the other two, which are simply a tree in which you can pass the record and simply verify the classification results. The decision tree is composed of the random forest is composed of multiple decision trees. And it is necessary to obtain the classification results of each and all of those trees before being able to obtain the final classification result, which is going to be the mode of all the previous results of the forests. Finally, we verified the parallelism of the immunity system, and we did this by increasing the number of nodes on the Pushback cluster, and then performing the classification test similar to what was done in the flow processing rate test. We verified that for most algorithms, increasing the number of nodes decreases the number of time necessary to realize the performance, the classification. The only case in which this not occurs is with the decision tree. Also, we can observe that the biggest impact happens with the random forest algorithm, which can be deducted because as said previously, the idea is that the model is composed of multiple decision trees, and this can be easily parallelized between multiple nodes. As such, we presented the NT, which is a precise, scalable, and real-time threat detection system. The system possesses two operation modes, which are online and offline. The offline mode, you can you store the datasets in a distributed manner. You can then create and analyze classification models using the datasets that you store, and verify the results through a dashboard in a to the visualization model. And the online operation mode, which collects data in real time through collects network data in real time, passes this data after being abstracted into flows through the float bag to the processing model, which then classifies the data through the classification models made in the offline model. And finally, the result of the classification also passed through a visualization model, so that the user can analyze the data, the network, how the network is being classified, how many attacks, how much data is being passed, among other things. We also made a performance analysis of the proposed system using a dataset containing real network traffic data, which, as I said, was collected from a major telecommunication operator. We verified through this analysis that the data frame API is significantly faster than the RGD1, that the decision tree and random forest and gradient impulse tree offered the best performance for the dataset we use, and we also showed that the Mini-NT offers a very high throughput rate, nearing 50 gigabytes per second. And finally, we showed the scalability of the system and how the system increases its performance for most algorithms by increasing the number of nodes. Thank you.
Thank you, Lucas, for presentation. So now you have time for questions. Lucas, can you open your camera to answer the questions? So please, if you have questions, indicate in the chat. So Marcelo, move on.
Okay, so let me start with the question while others think about their own questions. So, Lucas, thank you for the presentation. Okay, you proposed a nice system with a lot of contributions therein. My question is, what would you need to make this architecture a real system used in a real setup, like to make this become a product. What do you think you'd need as next steps to make this a product? I cannot hear. Maybe the mic is muted.
Lucas, you're not hearing you. Maybe your mic is muted.
It seems there is problem with your cask.
Hold on.
You can type your
Hello?
in the chat if you want.
Okay.
Okay, I cannot answer this, Marcelo.
Sure. Go ahead.
Okay.
Thanks.
I have never done a product, but I think that a product is very different from a prototype. I think therefore, as a prototype, it's near in the end. We have to do some improvement to make it faster. But to do a product, I don't know what I need to do a product. I only know that in between a prototype and a product, there is a lot of things to do. But as a prototype, we think that there is almost in the end.
Okay. This is a good answer. Of course, having a usable product is much further than the status you have today. But okay, the question also applies to what you said, that the prototype is nearly finalized, which is a good answer to that. Okay.
Hear me now?
So let's move to Gianni.
Hi, can you hear me?
Yes.
Oh, I have two questions. Thank you, Lucas, first of all. I'd like to know, I don't know if I missed it, but I'd like to know where did you get this data set and what it represents?
Can you hear?
It's very low, your sound.
Can you hear me now? I try to speak a bit louder.
A little bit better.
Okay. So about the dataset, we collected that dataset through we set a major telecommunication period. I don't know if you're allowed to say which one, but we collected it through the period of 1 week, and it contains real traffic data. We collected the data, and then for the machine learning part, we used the Pushback tool to abstract that into flows, because to be able to create classification models. Which was the other part of the question?
It was where did you get it and what it represents. Then I think you answered both. I have one more. Can I ask it, Igor?
Yes, go ahead.
Okay, so you used Suricata, right? For the IDS.
Yes, for the classification.
Then I would like to know if when you use this specific IDS, do you think you introduce some bias on the classification?
I don't know if you introduce some bias, or I know that our model is we need to labels to define what is attack and what isn't. So our model is going to be the capacity of our model to detect attacks is going to be limited by what the dataset contains, and the dataset is going to be was classified through that IDS. So in a certain way, our model classification, the capacity of classifying attacks is based on what the dataset offers. So in a certain way, yes, because we are going to depend on Suricata's classification.
Just a bit about this. It's Diogo speaking. When you use Suricata as the ground truth, your model will classify as well as Suricata at most. So isn't it better to use directly the Suricata IGS as classifier?
Yeah. We use the base dataset using Suricata's classification system, but we use other machine learning algorithms to make new predictions based on what Suricata offers. So we create new models based initially on what Suricata offers, but we're not necessarily tied to only Suricata. We use, for example, other datasets which use other IGS to classify them, and using those other datasets to create different models. Furthermore, our system was also developed so they could work on clusters and with dealing with big data in mind, which I'm not sure if Suricata particularly works with.
Okay, thank you.
Thank you, Lucas.
I have one question more. Andres, please go ahead.
Hello, can you hear me?
Yes, I can.
Yes.
Okay, so Lucas, first of all, a great job. I think the results are pretty good, pretty interesting. I'm not sure if I missed it, but I have a couple of questions. I think they're related to the features that you analyzed on the classifiers that you used. So the features were until which layer in the OSI model, where did you use in like the general features like number of packets, packet size, protocol flags, or you perform any type of deep packet inspection upon these data sets that you analyzed? That will be the first. Well, the second is related to the features that were extracted from those headers. So I think they're related.
Okay. We do not use the packet inspection. The features we use was extracted using the float bag tool. I don't remember all the features that they use, but they are, for example, the median times between the average size of packets, how much packets were in each flow. There were a number of features which there were a number of features. I don't have them in mind now. I could check later if you want to.
No, it's just cool. Thank you very much.
Thank you, Lucas. Thank you, Andres. So you move to the third paper, which will be presented by Andres, and it is called Access Control Policies for Network Function Virtualization Environments in Industrial Control Systems. The authors are Andres and Sandra Rueda from Universidad de los Andes, Colombia. So let's start the video.
Hello everyone, my name is Andres Murillo and I'll be presenting the paper Access Control Policies for Network Function Virtualization Environments in Industrial Control Systems. So industrial control systems, or ICS, are critical infrastructure for nations because they provide very important services to our society, such as electricity or energy, water distribution, management, and manufacturing processes. This means that attacks on this infrastructure have huge financial, economical, political, and even military impact. And we can see from the attacks that have been launched through the decades, such as the classic as Stuxnet, all the way back to attacks that are a little bit more sophisticated, such as the Black Energy attack against the Ukraine electrical grid, that it is an imperative necessity to protect and to ensure the systems. But what creates these kind of challenges? So the challenges to secure industrial control systems is actually inherited from the challenges of Industry 4.0, meaning that the integration of IT and ICS systems, more computational capabilities of industrial control equipment, and the integration of IoT and Industrial Internet of Things generates a series of problems that need to be addressed in order to protect the system. And this is that in Industry 4.0, the equipments have traditional devices that are running legacy protocols, which were designed thinking more about robustness and the capability to be operated under adverse performance conditions and not with security by the design and implementation of the systems, which creates that these protocols and equipment, they have a lack of protection because they were designed to run in isolation and to run in an environment where there was not a computational attacker trying to gain of them. And all the defenses of this kind of systems relies a little bit more on the attacker never gaining physical access with them. But by the integration of IT and ICS, attackers in many cases no longer need to have physical access to compromise the systems. This faces us with a lack of confidentiality, integrity, and authenticity in these set of systems. This means that we have all in working industrial control systems or in the CPS community, we require new technologies that can offer more security to ICSs without needing to replace most of the equipments and protocols that are already present in ICS infrastructure, because this equipment tends to be very expensive in the sense that they were designed to have very long life cycles. So a little bit of context and background into this paper is that I'm going to present quickly what an industrial control system looks like. So the first figure that you can see in the slide presents basically an industrial control system in which a plant composed of 2 water tanks is being controlled by 2 PLCs, 2 sensors, and a set of actuators. So what we have is that this is also a networked system in the sense that maybe the sensors are also network devices, but for sure the PLCs are endpoints or are network devices who send and receive messages and communicate through a sort of communication protocol. The difference being that the protocol they use to communicate tends to be an industrial control protocol. So we have 2 networks in the figure. The first one is what we call the field network. And in the field network, we have a couple of PLCs that are communicating with the sensors and the actuators using some industrial protocols such as Modbus or FieldBus. And then we have a supervisory network which connects what we call a SCADA server with the PLCs that are operating into the field network. And this SCADA is a server that basically collects all the information about the industrial control system and provides and presents it into a graphical user interface. Also, the company or the factory operators use the SCADA to monitor the behavior of the system, but also to configure set points in which this physical plant must be controlled. So the way that this happens is that using an interface, an operator configures the operation parameters. These parameters are sent to the PLCs through a SCADA server. Then the sensors measure the plant values and send the parameters back to the PLC. The PLC applies a defined control strategy and sends comments to the actuators. Finally, the actuators apply changes to the physical processes, and then the whole iteration cycle continues. So now the second topic that will be important for the paper is what we call network function virtualization. So in the traditional IT approach, what we have is that we have dedicated hardware physical middle boxes that were offering network functions. For example, a router. A router is a dedicated hardware middle box function that provides routing services. Meanwhile, a firewall could be a server that is blocking incoming ports or incoming traffic with certain characteristics. The Nfb approach, what it pretends is that instead of having physical middle boxes providing these services, we are going to use generic services that use or offer these network functions as virtual machines. And in this sense, instead of having dedicated hardware that using these kind of services, we will now have generic servers offering virtual machines. Why do we need NFB? We need NFB because it will bring, first, it will bring customization capabilities because now we can work with virtual topologies, which are by definition easier to adapt or to customize to a different environment. Second, we avoid proprietary hardware, which reduces greatly the capital costs, because instead of companies investing in dedicated physical middle boxes, they can now invest into generic services. Again, the other difference is inherited from cloud computational environments, in which we have now dynamic scalability, because we can adapt the traffic loads depending on we can adapt the number of virtual machines depending on the traffic loads that we have. And lastly, we have open source software which is being used in Nfb, which kind of helps with the interoperability. Now, we will talk about virtualizing industrial control systems. So some of these systems could be partially or fully virtualized. And the advantages that this brings us is that infrastructure can be dynamically adjusted if the control conditions change without having to modify the physical behavior of the system. In addition, we can virtualize the virtual ICS depending on the response of the system. Also, virtual ICS provides something that physical ICS cannot provide or fail to provide easily, and is that we can have them react and change the topology and the way they work if there is security incidents, because we can now, with virtual industrial control systems, we can dynamically change the network topology or take down a server and not replace it with a different one and do stuff like this. So in the community, this kind of virtual industrial control system is now being called digital twins, and we know that in addition to this, digital twins can also be provided as a very powerful cybersecurity research tool and optimization tool for this kind of industrial control systems. Nevertheless, if we're talking about virtualization of industrial systems, we're talking about sharing a certain pool of physical resources, possibly among different actors, which means that we will eventually need an access control framework that guarantees that the defined policies that we have are enforced and that the virtual environment keeps following a definition of security objectives. So this is how a virtual industrial control system would look. We have some equipment that by definition cannot be virtualized, such as the actuators and the sensors operating in the system. And then we have a virtualization layer, which this means is a virtual infrastructure, a cloud computing environment that virtualizes the different ICS equipment. This is where our virtual ICS or digital twins are being stored or are being working. And then on top of that, we have the operational service support or business service support layer, which have different ICS operators that possibly need to interact with the system with different roles and require a different set of privileges to work in one way or the other. So we did a survey, we did a research into the state of the art of the system, and we identified some necessities on Sdn and Nfb environments, but we found that access control still needs addressing. So we decided to pursue the access control for virtual ICS or for digital twins. So our proposal is to use or to create a framework that can provide and guarantee enforcement of user permissions. But in addition, we want to provide a very lightweight language that, without having a lot of technical knowledge into how to create complex policies, an ICS operator can first define how a virtual ICS is composed, and then define a set of roles and a set of enforcement policy and access control rules after he describes such ICS environment. So talking about access control frameworks, we have that an access control framework basically has two main components: the specification and the policy engine. So the specification refers to the resources, operations, and the users. That is what composes the industrial control system. And then the policy engine is something that we use to first express and define the way that that system works, and then have using a determinate language, and then we define some policies that should define the rules by which the operators of such system can participate. These policies tell to the operators or to the users what permissions they have to perform certain operations upon the resources available, and then we have a mechanism that must perform policy enforcement, that must guarantee that these policies are complied at all times. So in the case of industrial control systems or virtual industrial control systems, we have that the resources can be basically defined in three categories. The first are virtual industrial control functions, and what we call these are, so as we call that traditionally industrial industrial network communications can be virtualized, and instead of having a router, I can have a server offering a virtual machine. What we are arguing is that it is also possible to virtualize some ICS equipment. So instead of having a physical PLC, we could have a virtual PLC, which is something that has been proposed also by other digital twin projects. The second resource that we have is that we could have the traditional virtual network functions, which are virtual routers or virtual network middle boxes offering some sort of network service. And the last one is the network configurations. And we are talking about the software or the set of rules that define the behavior of a determined BNF. In the sense of the operations, we can split this in two, which are the BNFs related to the virtual resources per se, and the other one is the operations related to the network configuration. And lastly, the users and the roles are the virtual ICS operators that we have. So for ICS, what we would have, the framework that we propose is that first, an ICS admin expresses the policies using a high-level language, and these policies are stored into an access control policy engine using a high-level policy language, which ideally should be very lightweight, and then this compiles into a low-level policy, and to create these policies, we have the combination of the system specification, which is roles or users, operations, and resources, and then we compile these policies into some sort of enforcement system. In this case, when a user is going to perform an operation, depending on the role that the user has, this operation will be accepted or denied. This also means that the access control framework that we will be providing, that we are proposing, is based on role-based access control systems. So this is the policy language that we define, and we try to define a very lightweight policy language in which basically a policy is composed of a set of statements. And a statement can be, is in sense defined by different statements per se. A statement list is defined by different statements. So what composes a state? What can be a statement? What you can see in line 5. So a statement can be a role definition, or a category definition, or a network definition, or a permission definition. So what is a role definition in line 10? A role definition basically has to have a role, which has to use the keyword role, and then a certain name. And then between parentheses, we're going to put all the operations that a certain user or a user with that role can perform. Note that this requires that there's a predefined operation list stored somewhere. And the definition of the policies and definition of which operations are, we do provide a little bit of that into the paper, but that you can go and check out. But the definition of what should be the operations is out of the scope of the paper. On line 11, we have what we can call a category definition. And a category is basically a way of grouping different resources that behave more or less the same. So for example, a PLC is very expected that almost all the PLCs will behave in the same way. So the definition of a category is, for example, where I group different PLCs that should have the same role assigned to them, or should have the same permissions assigned to them, or share the same operations because, well, they are all PLCs. Then we have what we call a network definition. And a network definition can be a set of categories. I can create a network by combining different categories in the same sense. So we will see in an example in the following slides that, for example, I can combine the PLCs and the SCADA into a network, and I can create a supervisory network by combining them. And of course, a network can also be composed of different networks. Lastly, we have what we call a permission definition. In the permission definition, we have what we call the name of the permission per se, the role, and the networks to which this permission is applied. This means that we apply permissions based on the roles, and permissions are applied to networks instead of individual assets. And we try to do this to keep the language as simple as possible, and to be able not to have a lot of policies that apply to different end devices, but have a broad set of policies that applies to a category of devices. So an operation can be, for example, list, show, create, delete, update, attach, or detach. And that is basically the definition of the other things that we have. For example, basically a category can be either a category or a list of categories. And to define, for example, a network, we have the network or a network list. And to define a network, we basically have just the name. Now, for example, this is an example to kind of clarify a little bit these concepts. So note that in the same topology that I presented before, we have two roles. the operator role, and the owner role. So the owner can perform the operations create, delete, modify, and show because he's the owner of the whole ICS that we have. Meanwhile, the operator can only see what the configurations of the system are, and he cannot modify the topology that we have defined. Then we have three categories, one defining the sensors, LIT101, LIT201, and so on and so forth. Then the actuators, we group all the actuators in the same sense, and then we have the PLCs. And then using this category of sensors, actuators, and PLCs, we combine them and we create what we call a network, which is called a field. So this would be a field network. Line 14 and 15 define a couple of categories for a SCADA system and for the historian, and then we combine these two into what we call the supervisory network. So the supervisory network is composed of the SCADA and the historian. And lastly, we define the whole system as a virtual ICS by combining the network's supervisory and field network. So up to line 21, we have defined what are the roles, what the operations can perform those roles, and what is how the system is designed, or how we have specified the system. What's missing now in lines 24 and 25 is to assign a user to a specific role and to a specific resource. So the lines 24 and 25 are the ones that lastly assign the user the permissions that we have. So using this topology, we implemented a simple use case, and basically this use case was implemented, or a proof of concept. This was implemented using OpenStack, and we chose OpenStack because it's an open source cloud provider service that can be customized to the necessities that we have. And in the case of OpenStack, we implemented a virtual ICS topology, and basically what we did is that we took a mini CPS, we created a virtual image that uses mini CPS, but does not require Mininet. So all we're doing is that we're having the API that mini CPS offers to have industrial protocols implemented on top of them. Now, we choose also OpenStack because OpenStack has a service called the Oslo Policy Service. And the advantage of using Oslo is that it provides total mediation in the API calls that are performed in the virtual ECS. And Oslo now, he depends on having a JSON policy file for each one of the services that they have. Some of those who are familiar with OpenStack will know that OpenStack has a set of services, one providing virtual machines, one providing network, one providing storage, and so on and so forth. So each one of these services has a policy.json file. So every time that an API call is done, every time a user is trying to do something in OpenStack, this policy file is going to be checked. So what we did is that we extended this policy file in order to centralize all the permission enforcement. So whenever you have a permission that needs to be enforced, what we did is that we used an AND logical operator and forward that request to our policy engine. So that policy engine, using the URL, we just tell him which operation is performed and then the URL engine uses the tokens that are delivered when these API calls are made to define the permission that the user can do. So this is how it works. First, we have an admin that writes the high-level policies. Then we translate that into our low-level policies, and then we add all the modifications performing the policy.json. Then, when a user tries to access a service through the API call, this that policy.json is checked, and then that is forwarded to the HTTP server, which is our policy engine, and that operation returns a true or a false, and then the Oslo service performs the deny or the acceptance of what the user did. Finally, we have the discussion and the contributions that we have, which is we define an access control framework for industrial control systems. We provide a way of specifying the resources, operations, users, and roles for future work that are performed into access control frameworks for ICS, either they be virtual or physical. Second, we provide a high-level policy language that can be used to define enforcement mechanism rules for access control in ICS systems. Third, we provide a prototype implementation in OpenStack, which is open source and available in the paper is the link, and in the slide at the end of the presentation will be the slide available. So the conclusions is that we implemented a proof of concept that uses OpenStack for provide access control for virtual ICS, and our language enables the administrators that do not have a lot of technical expertise and can define using very simple rules operation enforcement mechanisms or access control rules for virtual industrial control systems without, and what we wanted to do in this work was to avoid having very complex rules or very granular rules. As future work, we envision that there can be policy conflicts that need to be addressed also. So we would need to have policy conflict resolution algorithms for this kind of virtual access control frameworks. Thank you very much. Questions and comments are always welcome. That is in the slide. There is my GitHub profile, but also there's the UniAndes or my university GitHub profile where you can get a copy of the proof of concept that we performed. Thank you.
Thank you, Andres. Let's move to the questions. Can you open your camera, please? So you have time for a few questions. So I have a question.
Yes.
About the whole of Oslo and your solution. How can you develop the solution without Oslo, or how hard it would be to develop the solution without this part of the system?
Yes. So if you were to implement this without using Oslo, you would have to basically implement by yourself all that we call a reference monitor. So there will be a two steps work into that process. The first one is to using whatever provider you have that is providing the functions that you're trying to basically control. For example, create a virtual network, modify a virtual network, launch an instance, copy a virtual machine, or perform any sort of operation upon the virtual infrastructure. You'll have to implement what is called hooks. And that is basically you'll have to instrument add some instructions into the code providing that basically stops the operation and requests or forwards the authorization to another module or another service. And then you will have to implement a monitor that actually forwards to the one that we are developing. That was the main reason for choosing Oslo, because in this kind of access control frameworks, you want to have two properties. The first one is correctness, and the second one is completeness. And Oslo provides completeness in the sense that all API calls are mediated by the Oslo. I mean, they are mediated by the Oslo service if there is a policy JSON file present. If there's not a policy file present, then the policy is not parsed and all the operations are uncontrolled. But if there is a policy JSON, then there exists that mediation. So for you to implement this, you will have to do two things: the hooks into the functions and the forward into the service. You don't have to implement it on all the operations. Perhaps you could identify some functions that are critical and require total mediation by an access control framework.
Okay, Andres, thank you. Joe has a question.
Hi, Andres. Thank you for your presentation. It was a very nice presentation. I just have a simple question. When you say that you are using a virtual ICS, are you virtualizing the PLCs, or you are just virtualizing the applications that you run, getting the data from these PLCs?
Okay, that's a good question, because when we did that work, the area of digital twins had not gained that much momentum, I think. But what I say now is that we should virtualize the PLCs. We should virtualize not only the applications, but the kernel that is in charge of receiving the sensor inputs, applying whatever control logic you have. In the case of our experiments, the control logic is very simple enough, and then virtualizing the outputs. Then again, there are two things there. The first is that you cannot virtualize anything. A PLC has certain interfaces that require an electrical voltage or electrical current that is not available on a generic server. Generic servers have network interfaces, USB ports. Some ports like this, they don't have, for example, 4 to 20 milliamperes. So you would need to have this part of hardware added to the server. And the second one is all the questions related to providing real-time requirements, which I think is an interesting research area for virtual networks, and is can we build a hypervisor that provide this kind of real-time warranties? Because the problem that we need to address if we want to virtualize the PLCs is that we have to provide these guarantees. And for some systems, such as water systems, we kind of guess that it's going to work, because if the water plant has a response time of a minute and we are running this on top of a very powerful server, then we expect that in that minute it will be able to perform a lot of calculation cycles. But we do not have a guarantee of that. For example, what happens if our software hangs up, if it's a deadlock, if it's something like that blocks it. So when I say virtualize the PLCs, I not only mean the applications, but also the whole kernel that provides the PLC functions.
Thank you, Andres.
Thanks to you.
So thank you, everyone. This is the end of our first technical session. Let's thank you again, all the presenters and all the audience also for the questions. So in a few minutes, you have our first tutorial. Marcelo will be the chair of this tutorial. So in 5 minutes, we will be back with the tutorial. Okay? Bye-bye, guys.
Okay, everyone. So welcome back to CIoT 2020. I think now have enough people back to start our first session on tutorials. So the first tutorial will be on scalability of LoRa networks for dense IoT deployment scenarios. And Professor Pham will give us this tutorial. Just before giving the floor to him, let me just say a few words on Professor Pham. So he's currently a full professor at the University of Pujolle. And you have all the details of his bio on the website. But in a few words, I'd like to say that Professor Pham has a huge experience on IoT in general, and has been given several tutorials and keynotes in the areas of IoT, and specifically on PWAN network. So I'm sure, guys, that you enjoy a lot his talk. Has a huge experience, so don't hesitate to make any questions. I'm sure the audience will be very happy with this tutorial. So without any further ado, let me give the floor to Professor Pham for his tutorial, and then we'll have some time for questions and to interact with our speaker, and to be sure that you understand everything about scalability of LoRa network. So Professor Pham, the floor is yours, and let us learn everything about these technologies.
Okay, thank you, Marcelo. Do you hear me well?
Perfectly.
Okay, that's
Thank
great.
you.
And so the screen sharing is okay, right?
Yes, it is.
Okay. So thank you for all this introduction, and actually you put a lot of pressure on me. So let's see what I can tell about scalability of LoRa networks. And first of all, I just want to show where I am right now. And so with the video conference, we probably don't know where exactly people reside. I'm very happy to be with you for these remote tutorials. Also, when I check the weather forecast, I believe that I would rather be close to Rio right now, because we have a very rainy day today. And so I don't know how many persons are in Brazil right now, but they're probably more lucky than me. So let's start with the first, the low power and long range radios, and probably many of you have heard about these LP1 networks, and they try to cover an area where I don't see if you see my mouse when I move the mouse pointer.
It's very small, but you can see if you are very careful.
Okay. Okay. So so if you're looking at the wireless networks ecosystem, so we try for many years to optimize the data rate, having more and more data rate, and we try, of course, to have more long range, but there's the big dilemma about the energy and range issues. And obviously, if you want to transmit very far, then you're going to consume a lot of energy. So very recently, as you can see, there's a big area that have been left unused here, where you have normally very low throughput and normally very high range. So very recently, we have the so-called low power, long range radios. And there's many candidates, maybe 5G, maybe narrowband IoT, when it comes to real deployment. But these last 6 years, about 6 or 7 years, have seen tremendous interest in two proprietary technologies, Sigfox and Sigfox and LoRa, and they have been around for about 6 to 7 years now. So they are quite early with the proposal of 5G that are just beginning to be deployed, to be rolled out in a large scale right now. So actually, there's a whole ecosystem behind these networks, and it's quite interesting to see what will be the issues when we are going to deploy more and more of these networks for IoT. So very quickly, the expected range that we can that we want to have with these technologies is in the range of 30 kilometers, 20 to 30 kilometers. And regarding the power consumptions, would be between 15 and 40 milliamps. So compare with cellular networks like 3G or 4G, the consumption is much smaller than the low power terminology. Of course, the price to pay is very high because the throughput is in the order of bit per second. So you're not misunderstanding bit per second. I'm not talking about kilobit per second or megabit per second. It's really bit per second. And for instance, if you want to send about 20 bytes, indicating, for instance, the temperature and the humidity level, then the time on air, meaning the transmission time, can be as high as 1 second and 44 seconds, just to send 20 bytes. But you expect this message to reach a gateway that can be in the range of 20 to 30 kilometers. So when we look at these, the three major technologies right now, which can be Sigfox, LoRa, and Narrowband IoT, when you compare the range, we can see that Sigfox has better range. 40 kilometers for rural, 10 kilometers urban. LoRa is a little bit less, 5 kilometers for urban, 20 kilometers rural. And narrowband IoT is obviously the less efficient in terms of coverage, only 1 kilometer urban. Fact is, narrowband IoT is more a cellular network technology. So most of operators that are deploying narrowband IoT, they count on or they rely on the high density of base station. So they expect that the distance between two base stations or the distance between the base station and the narrowband IoT devices can be less than 10 kilometers in rural and hopefully less than 1 kilometer in urban. So the goal is completely different compared to the two other technologies that can be denoted as true long range, whether the narrowband IoT is not that long range, but probably has more coverage and more performance because of the rollout deployment scenario. Well, there has been a lot of coverage tests performed during these years, but it's always funny to do your own tests, and we were quite lucky last years to be able to install a gateway on top of this building. Unfortunately, we wanted to take this building or this one, but we were not allowed to. So we took this one, and this one is about 100-meter height. And we also travel around the cities, and we were able to get some kind of 8 kilometers in urban area. See this point here, 8 kilometers from the gateway. But we easily got 3 to 4 kilometers without any problem. And so we traveled to the mountains area here, and you can see that there's some kind of mountain. And if you measure the distance between the peak of the mountain here and the gateway, we were at 26 kilometers. So it's quite very promising, because you're transmitting with a power that is as small as a Bluetooth power, and you can have a 26 kilometer range. There's a lot of effort also in trying to push LoRa technologies for satellite, because there has been some early high altitude ballooning tests, and my colleague Fabien Ferraud from University of Nice, he also did its own test with a balloon, and he managed to reach 31 kilometers. and the longest reception was more than 600 kilometers away. It's not the record. The world record is about 700. Probably it's increasing maybe to 800 kilometers now. I'm not up to date with the latest record, but it means that actually, if you consider like 400 or 500 kilometers range, you can already reach a low orbit satellite. And we've seen in the previous keynote that satellite is going to play a major role in providing internet, worldwide internet. Here, there's a lot of expectation using LoRa to reach satellite, low orbit satellite, in order to provide worldwide access or worldwide IoT connectivity. So that would be great to be able to connect, or to send data from everywhere in the world using very low cost satellite. Obviously, when we move from the traditional short range technologies such as 802.15.4 that the research community has been using, or many industry has been using all these years, moving from short range to long range typically change the way you are deploying a whole infrastructure. I would say that maybe we have to forget multi-hop routing, because as we can see, when we were in the multi-hop research, very few operational networks actually use multi-hopping, because when you exceed 2 to 3 hops, it's going to be very complex to manage, especially in terms of scheduling all these relay nodes so that they can be awake at the same time in order to relay your packet. So it was very complex to set up such an infrastructure. So when you move to low power wide area networks, and the typical scenario or the typical topology is really gateway centric. You may have an extended star topology, but usually the main topology would be the star. So the complexity of deploying such networks, such infrastructures, is very low. Now, let me try to give you some insight on actually how these technologies, how these radio technologies manage to increase the range. We know that increasing range can be done in 2 ways. The first way to do it is to increase transmission power. So you probably all know that if you speak louder, then people can hear you on a longer range. But in many cases, it's very difficult to increase the transmit power because of regulation first, and then of power consumption. So if we're talking about IoT battery-operated devices, then of course transmitting at a higher power means much higher energy consumption. The other way is to improve the receiver sensitivity, so that the receiver can decode the signal even when you have a very low power signal, when the receive power is very low. So one way to do it, because there are several ways, but one way to do it that are taken by most of these long-range radios is you can increase the robustness, thus the sensitivity, by transmitting much slower. Just like you're speaking much slower when you want to be understood by somebody somebody far away. Okay, so LoRa typically uses a spread spectrum approach to increase the receiver sensitivity, and the way it's doing that is defining how many chips will be used to code a symbol. And you can see in the table here that you can have spreading factors from 6 to 12. And if you see, for 12, for a spreading factor of 12, then you will have 4,096 chips per symbol. So it makes a LoRa symbol very long, okay? So that explains the very low throughput when you are using the longest or the highest spreading factors. So you can see in these graphics here that when you're increasing the spreading factors from 7 to 12, then of course you're going to reduce dramatically your throughput, going to few hundreds bits per second, and you can decrease or increase, you increase the received sensitivity by having a minus 136 dBm sensitivity. So that's one way to do it, and this is the way LoRa is doing it. And if we looking at the spreading factors as a chip rate, then we can see in image that longest or highest spreading factors mean that your signal is going to take a lot of time. Okay, so the slope here is not very high. So you take much more time to transmit one thing. Okay, so this is the way we can see the spreading factors in image. LoRa is using some kind of, I'm not going into much detail, okay, of the physical layer, but I just want to give you some basic information on how it works. And LoRa is going to use what we call a chirp spectrum modulation. So a chirp is a signal which frequencies varies over time. It has been used a lot in radar system, and LoRa took this old idea and put everything together in order to have a robust system. So when you are adding the spreading factors into this processing chain, then actually your chirp is going to take more time. Okay, so you increase the receiver sensitivity by having more spreading factors here. And a LoRa signal can be seen as an up chirp or a down chirp, depending how frequency is going to change over time. And what you are coding actually is how you change from one frequency to another frequency. See here. So you see how the modulated signal is going to code the 1 and the 0 of your digital communications. So I'm not going to spend more time on the physical layer, but just want to point out that the advantage of spread spectrum is usually compared to the regular narrow band, or to compare to the regular large band, but not ultra large band signals. Then the spread spectrum techniques has a unique ability to be able to decode the signal below the noise floor, and LoRa did this very, very efficiently. And if you can see here, when we're using the highest spreading factors, then we can have a minus 20 dB with regard to the noise level. Yeah. So that's a lot. Okay, traditional radio systems such as Wi-Fi, for instance, needs to be much higher than the noise floor in order to be able to decode the signal. So here it's a huge improvement that these long-range radios offers to the communication ecosystem. So if you want to know more on the physical layer, on how this modulation is realized, then I've provided some links here. And I will give the presentation, so you will be able to download it if you want to have all this information afterwards. So how can we explain the success of LoRa? First, of course, the long range, the low power that enables 5 to 10 years of battery operation. And probably one reason is also because you can have fully ad hoc deployment of device and gateway. Remember, I told you that there are two competing long-range technologies. So this talk is going to focus on LoRa, but we should not forget the other one, okay, the Sigfox, which is also highly deployed. But right now, I mean, there's probably more LoRa deployment because of the choice LoRa adopted for deployment that allow completely private deployment network or LoRa networks to be deployed. And currently, even there's some public deployment, some LoRa network has been rolled out by operators, Orange, Bouygues Telecom, and probably others around the world. A lot of LoRa deployment are still currently private, including companies or whatever. Okay, so that explains a lot the success of LoRa. So there's a huge availability of low-cost radio systems, and the whole do-it-yourself IoT ecosystem also have produced a lot of nice IoT devices for hobbyists or tech enthusiasts, and some of them can be as efficient as commercial products. And of course, given all these reasons, then there's a large choice of commercial products. And if you go to the, if you search on the web, IoT, LoRaWAN devices, then you can see these great devices, very integrated, adapted to a lot of usage, and most of them are plug and play. So it's very nice to play with this kind of technologies, because in 10 minutes you can have your IoT pushing data to clouds and getting the data on your smartphone. So it's quite a mature ecosystem. So on top of the LoRa physical layer, you have what we call the LoRaWAN alliance, and LoRaWAN should be seen as let's say, a link layer specification. Okay, so it tries to add some control command in order to control a LoRa physical network. So the typical architectures of LoRaWAN networks is to have LoRa between device and gateways, okay, following some kind of packet format. And then you have the gateways connected to internet and then sending to application servers, sending to network servers, and so on. So it's, let's say, a typical distributed system where you have the gateway that are connected to the internet. So nothing new behind the LoRaWAN. But what's very interesting is there has been a lot of initiatives from many organizations trying to deploy public, open source. Some of them are open source. Most of them are public LoRaWAN network servers, so that you can roll out your own LoRa networks without having to worry about installing application servers or network servers. And everything is taken care for you. And as I said, I mean, if you configure your gateway and if you configure your device, you can have a whole infrastructures deployed in less than 10 or 15 minutes. So that's a huge step forwards compared to what we have to do previously to set up a whole IoT infrastructures. When we talk about the requirements regarding LoRaWAN gateways, and these gateways should be able to listen on multiple channels, and they do this by most of them using the SX 1301 radio concentrators. So these are the frequencies, I mean, the standard frequencies. And the nice thing is you can listen on several spreading factors. So we have been deploying also do-it-yourself gateways, and in doing that, you can produce very versatile IoT gateways, and this is probably the added value when you compare to commercial gateways. Now, let's go to the core of the talk after this introduction to LoRa, just to set up a little bit the context. How we solve the device gateway connectivity issues with LoRa? The fact is, we are going to deploy LoRa in a very dense environment, where there's expected to be a lot of gateways and a lot of interference from other technologies as well. So let's try to dig into what we call deploying in dense environment. Right now, it's currently deployed in unlicensed band. Most of the deployment are sub-gigahertz, but because of the very difficulties in having a common frequency band all around the world, then LoRa is also currently existing 2.4 gigahertz. So when you're adding more device, of course, you're going to have more traffic, more interference, and more collisions, okay? But usually, you are adding more gateways. And by doing that, you typically increase packet reception rate in a very great manner. The only downside or the only drawback right now compared to a cellular network is you have no roaming right now for low power. So if you are bound to a given network server, then there's currently no exchange of data between network server belonging to several providers. Probably this is going to change. I don't know how they're going to do it, or I don't know what will be the business model behind this. But typically, this is something that is currently limiting the usage of IoT device all around the world. Because if you want to change providers, or if one of your providers is not present then in your country, then it's going to be a big problem. So I'm not going to talk about this. I'm more talking about there's going to be more gateways, so definitely the packet reception rate is going to increase. There are a number of low-level mitigation techniques. There are a number of mitigation techniques. So I'm going to present first the low-level mitigation techniques, and then we're going to look at the higher-level mitigation techniques. So first of all, the first mitigation technique is the orthogonal of chirpiness. Actually, the spreading factors, as you can see, previously define a chirp rate. Okay, so the larger the spreading factors, and the chirp rate is the lowest. And these different chirpiness provide some kind of orthogonality, meaning that if you're using the same frequency, okay, and if you're using the different spreading factors, then your various communication using these spreading factors then could be considered as almost orthogonal, meaning that and decoded at the same time. So LoRa has 7 spreading factors, 10 different bandwidth. Okay, these are the mostly used. 125, 250, and 500 kilohertz are mostly used. You have smaller bandwidths, but given the fact that with 125 kilohertz bandwidth, you already have very, very small bandwidth, then just imagine the bandwidth you have with lower bandwidth, the lower physical bandwidth. So most of the bandwidths we use right now are probably 125 kilohertz. This is the first, let's say, interference mitigation technique that is offered by LoRa. The fact is, it's not always orthogonal, because what we are looking for is the chirp rate, okay? And this chirp rate, the way LoRa modulation is done, is defined by bandwidth, the physical bandwidth, times the symbol rate. So we ended up with these very simple equations, and it shows that if you have combinations of spreading factors and bandwidth that give you the same chirp rate, then it's not going to be orthogonal. So we can try to avoid this combination. So all the combination marked in red are non-orthogonal, and all the others are orthogonal combinations. So as you can see, even if it's not almost perfect spreading factors orthogonality, you still have a lot of combination that gives you orthogonality. The fact is, when you want to have the longest range, you have to use the smallest bandwidth, 125. Okay, so if you look at the square here, 125 kilohertz, then you have some combination. You have a reduced number of combinations, but still you have many combinations that provides orthogonality. One other mitigation, low-level mitigation techniques is the frequency diversity. A gateway, I mean, a real LoRa gateways, real LoRaWAN gateways, has to listen on 8 channels. Okay, so you can have 8 different channels. So some studies shown that, of course, you're going to have a lot of collisions if you are sending a lot of message. Okay, well, 100 messages per minute, it means already 1 message per hour per device, and that means 6,000 devices in the vicinity of one gateway, and it's only for one frequency. Okay, so if you're using the whole range of frequency, then obviously the packet loss rate is not that big. Okay, in a real deployment with a real gateway. So when we're looking at the theoretical results, it may show that a lot of packet can be lost, but I mean, practically with 8 channels, then you have a lot of frequency diversity. And so at the early beginning of LoRa, a lot of people said, okay, LoRa is very similar to an LoRa system. And we all know that LoRa system efficiency is about 18%, okay, because you have contention windows, and the contention window is more than the time of the packet itself. It's more like 2 times the packet window. And then we try to I mean, of course, the LoRa system can be improved to slotted LoRa, and we have an efficiency of about 40%. But do we really have LoRa equal LoRa? This is what we thought at the beginning, but actually a lot of studies have shown that because of the way LoRa modulation behaves, there is capture effect, and capture effect has been known for many years. And capture effect means that in some cases, even if you have overlapping transmissions, then you can receive one of these transmission. Okay, so it can be the first, can be the second, depending on the transmission power. And so right now there's a lot of studies on what we can achieve with LoRa when we take into account the capture effect. And provided that you have a power difference between 2 LoRa signals, then you will be able to observe the capture effect. So even if you have an overlapping of the transmission, and in many times you can have a huge overlapping, not only the beginning or not only the end of the transmission, but sometimes most of the transmission is overlapping, but still you are able to decode one or the other messages. So we did some tests in capture effect in practice. Okay, so now in the lab we had a real deployment around the campus, and we have 20 meters here, 100 meters here in outdoor environment, and we observed actually the benefit of the capture effect. And if we have a difference in transmit power, I mean, a small difference in distance is still enough to have this difference in signal to interference ratio that allows you to see the impact of the capture effect. So here, most of the receive comes from the master, and once you increase the distance, then sometime, or when you reduce the spreading factors, then sometimes you can receive a little bit less from the master, a little bit less from the slave. But in most of the case, we observe a successful reception of one of the packet. So actually, if we try to put everything all together, there's interesting studies showing that, okay, so this is what we believe LoRa was, okay? The red one. What we believe LoRa was with modeling the system as a pure LoRa system. And actually, this is what this is losses, LoRa losses, and this is actually what we have taking into account capture effect. So you see that the decrease in percentage of packet loss is quite huge. So the conclusion is, okay, LoRa has currently no MAC control or listen before talk, nor carrier sense mechanism, but thanks to the capture effect, then already it's behaving much more efficiently than an LoRa system. There's advanced signal processing that are quite promising. I'm really not a specialist of successive interference cancellation, so this is research I reported from the literatures. And normally, theoretically, successive interference cancellation can be applied to LP1. So there have been simulations, MATLAB simulations, showing that you can try to decode the strongest signal and then remove this signal from the overall signal, and then with the remaining signals, then you try to decode the strongest signal again, and then you're doing that iteratively. And in doing that, theoretically, it can be you can decode several transmissions that have been performed at the same time. Okay, so this is quite promising. Right now, however, this is more theoretic. Probably some lab experiment has been conducted, but the real experimental on real deployment, LoRa deployment, are yet to be realized. So I won't be able to give more detail on this. I just want to mention that there have been some attempts in doing that. So if we manage to make successive interference cancellation successful, so probably it will provide another jump into performance of these LoRa technologies. So these are simulations. So if we try to combine capture effect and successive interference cancellation, then of course we ended up with a theoretical or hypothetical system that is well beyond the LoRa system. Okay, so the LoRa is here. Okay, and if we are successful in adding capture effect and capture effect with successive interference cancellation, then as you can see, the throughput and the success probability can be much higher. Now, let's talk a little bit more about the high-level interference mitigation techniques that we can have. They can be separated in three categories. Could be policy-based. So policy-based means regulation from organization, standard organization, or government. Okay. So most of the policy-based impose some kind of duty cycling. Okay, so 1 second duty cycling, 1 person duty cycling, for instance, so 36 seconds of transmit time every hour. This is for Europe. In the US, I mean, the limitations are very, very strong. I mean, the limited dwell time is 400 milliseconds. You have a lot of frequency hopping that you have to do. Okay, it is mandatory. So LoRa in the US is very challenging, and this is why, because of the dwell time here, of the maximum dwell time, then spreading factors are limited to 10. You're not allowed to use spreading factors of 12, because then the transmission time of a single transmission would be too high. So this is a kind of regulation that can be categorized as high-level LoRa interference mitigation techniques. And of course, the specification itself can impose some constraint. LoRa won't typically enforce what we call as radio inactivity time. So each time that you are transmitting something, then you are forced to remain silent for a given period of time. Okay, so that tries to have some kind of fair access to the channel, because the whole sub-gigahertz unlicensed band is pretty crowded. And of course, you want to administrador do fundo. Então, sorry. Hello. Is there any question? Do you hear me?
Yes, go ahead, Kunduk. Maybe there was
Okay.
a mic that was unmuted with no
Okay.
intention to interfere.
Okay.
Go ahead, please.
Okay, no problem. I thought it was a question. Where am I? Okay, the specification, and then you can also have some ad hoc mechanism, advanced ad hoc mechanism, and this is quite interesting because here we cannot do anything. Okay, regulations are regulations, and probably maybe they're going to change because IoT is going to be so important. And it's a source of revenue for a lot of countries or a lot of companies and governors also. Probably regulation is going to change some days. Right now, there's a lot of margin here to try to have a priority scheduling, resource allocation, try to have TDMA-like and so on, or listen before talk and carry send. So we're going to go back to these issues a little bit later. Yeah. So there's a huge impact of the frequency plane because if you follow the some kind of standard, you have to use the frequency so that device can talk to gateways. Obviously, you have to set up some kind of frequency plane. So any frequency plane is going to increase interference level, of course. But the fact is, we see more and more channel gateways with more and more channels. So the basic requirement was 8 channels, and we're going to see, we already see a lot of 16 channel gateways. And it's not unrealistic to foresee 24 and 32 channel gateways in the very near future. Okay, I haven't checked recently, so maybe we already have a 16 channel. Sorry, we probably have a 24 channel right now. Maybe I don't know it, but for sure there's already 16 channel available. So actually, as the number of IoT devices going to increase, then we are going to increase the number of frequencies handled in the gateways. It looks more like the whole discussion we had many years ago regarding quality of service. A lot of operators, they are over provisioning with optical fibers. So here it's approximately the same behavior, okay? So when we observe some kind of frequency limitation, then we're going to increase the number of frequencies. So this is something that we already observe and is probably gaining more and more interest in the future. And so when we take everything and put everything all together, the question is there something new under the hood? Probably not, okay? A lot of these mitigation techniques already exist, okay? Capture effect, we know that it exists for many times. Orthogonal transmission, so spreading factors could be seen as a code. So we know CDMA for many times. So I mean, providing orthogonality in transmission is not new. We know that if we have a gateway-centric system, then scalability is directly linked to the number of gateways. So if we increase the number of gateways and if we increase the number of channels, then we automatically increase the number of devices we can support from a gateway. So a simple calculation on 6 spreading factors, 16 frequencies gives you 96 logical channels, about 200 devices per logical channels. You already have more than almost 20 devices per gateway. Okay, so this kind of numbers show you that you can increase linearly you can increase scalability quite easily with this kind of system. The fact is, we also expect LoRa has a unique, I would say, a lot of private personnel, private meaning people like you and me. I mean, not operators. They are actually installing their own gateway. I mean, some of them are single channel gateways. So say only listen to one of the channel, not the entire 8 channels, but anyway, if you already deploy, let's say, 100 or 200 single channels, then it's definitely increase the gateway density. So the fact is, you can buy an indoor gateways for less than 200 euros. You can make yourself a real 8 channels gateway, do it yourself 8 channel gateways for less than 150 euros. And you can have a single channel based on Raspberry for, let's say, 45 or 40 euros. Okay, so this is just unbeatable. The price is very low. So a lot of people are deploying that, and linked with the community deployment of LoRaWAN networks, such as the Thin networks, TTN. Then we had a huge number of gateways out there. Okay, so there's a very high probability if you buy a LoRaWAN device from the market, or if you build one and then you switch it on, then there's a high probability that your transmission is going to be catched by a gateway out there. Could belong to an operator, could belong to somebody, but there's a high probability for your transmission to be caught by gateway. So if we're talking about dense gateway scenarios, of course, some gateways will be closer to devices that allows you capture effect to happen. Okay, so the more gateway you deploy, the more you increase the probability of capture effect to actually happen in your system. So that's a good thing, because even if capture effect needs some kind of power difference to really work, the fact that one device at one point, at one moment, will be closer to a gateway than another anyway. So capture effect has high probability to be successful. And then I'm going to finish. I mean, try to. I think that I'm running out of time, right? I mean, a little bit. So in 5 minutes, I'm going to try to end my talk here. I just want to talk about a little bit about CSMA. Do we have to forget CSMA, or can we implement some kind of CSMA or listen before talk? In other traditional radios, CSMA is definitely needed to really avoid collisions. Okay. The fact is, in LoRa, trying to add some kind of listen before talk or CSMA, carry sense mechanism, can be very challenging, because all these low power wide area networks technologies, they are spread spectrum, and then you can receive below the noise floor, as I said before. So when you want to perform a channel activity detection for assessing whether you have a clear channel, sometimes it works. Okay, so the scenario here, it works fine. During a whole transmission, you can detect that you have activity, but sometimes you cannot detect. And when distance increases, then you have something similar to the hidden terminal issues that we all know. And when you try to perform a channel activity detection, then many times it happens that you're not detecting anything. Okay, and sometimes when you are far from the gateway or far from the transmitter, in our case, we were in the university areas, and when we move more than 1 kilometer away, then we started to have real issue with the activity detection. Okay, because the procedures to detect whether you have activity on the radio gives you a negative answer. Okay, it says there's nothing on the channel, but at the same time, okay, we have a device performing the CAT here, but at the same time, we have a gateway here that tries to receive a packet. So actually, we detect nothing, but the packet is received. So the sensitivity of reception is higher than the sensitivity of the CAT procedures. So it means that the whole clear channel assessment is pretty unreliable using these spread spectrum regions. So we try to propose something using this unreliable, and we were a little bit successful, I would say, to protect longer message, because if your message is very long, then the probability to have at least one successful CAD is higher. Okay, so we were experimenting in image transmission using LoRa. And for image, since the amount of data is a bit higher, than the packet is much longer, so you increase the probability to have a successful CAD. But of course, this kind of approach that definitely has its limit, because if I go back one slide, after 1 kilometer, then we have nothing. Okay, we really have nothing. So it means that in this case, we don't even have this dot here. So a whole transmission can be unseen by another transmitter. So if we go back a little bit using the capture effect, because we dig a little bit more, discovering that the CAD is very unreliable, we try to perform more tests on the capture effect. And we try to see the relationship between the overlapping and the preambles of the packet. So using spreading factor 12 and bandwidth 125, the preamble of the packets is about 400 milliseconds. So what we did is we took two transmitters, one gateway, and one transmitter start at T0 and the other transmitter start a little bit with delay. So 100 millisecond delay, 200 millisecond delay, 300 millisecond delay, 400 millisecond delay, and more. Okay, so we can see here 100, 200, and so on. So what we observe is if your transmission overlaps during the preambles, then if you overlap at the very beginning, then B wins, because you are completely destroying the signal from A. And then the gateway is going to be locked on transmitter B. But after that, sometime A wins, and most of the time A wins. But if your transmission is overlapping after the preambles, then most of the time A wins, regardless what transmitter B is sending. Okay. So actually, what we observe is ALOA that bad? Because if we look at the curve here, you can decide to transmit whenever you want. Okay, because if you transmit here and you interfering here, then you win. If you're interfering here, then at least 50% of the packets can go through. And if you're interfering after the preamble, so after 400 milliseconds, then that's fine. One packets managed to go through. Okay, so this is probably a little bit awkward as a question for us scientists to say that actually ALOA system for LoRa, when we add capture effect on top of it, it's going to be quite good. Okay, it maximizes packet delivery rate because you are not delaying the transmission. It reduces latencies, but of course it's not very energy efficient, because a lot of transmission is not going to be received. But from one device perspective, probably it's better to send following an ALOA system. Okay, so let's see how it goes. Probably that we need more studies to confirm that results, but the choice of not going any listen before talk mechanism on LoRa probably comes from the fact that it's very difficult to find or to detect a clear channel assessment. So I'm reaching my conclusions. So the fact is, I don't want to say that LoRa is perfect or whatever. Okay, of course LoRa is good because it has very unique features. And I try to show you why it is good and why it has some features that helps him to be able to scale to a lot of dense deployment. And probably what is going to really change or to really contribute is, I believe, the density of LoRa gateway. Okay, density is going to be very high in cities. Okay, because of lots of deployment, and probably also because a lot of people are going to deploy their own gateway. Okay, if LoRa can be integrated into, let's say, DSL boxes, and there are some studies trying to do that. When you have a DSL box in order to provide you internet access, and you have at the same time a Pico LoRa gateway, then of course the density of LoRa gateway is going to be very high. And also one thing that helps that I want to emphasize here is the frequency diversity offered by the gateways. Okay, 16, 24, and probably 32 frequency. So that ends my talk, and I hope that you enjoy it. And thank you for your attention. And I'm ready for any questions.
Oh, thank you so much, Conduc, for this very nice and complete talk. I'm sure there will be a few questions. I have myself some, but I'll let the folks make questions first.
Okay.
Please, guys, if you have any questions, just raise your hand or let us know through the chat.
I have a question.
Yes, I can see that, Andres.
Hi, Pham.
Hello.
Long time ago, I met you in Paris. Do you remember that?
Okay. Oh, that's great.
Okay. What you are saying is that LoRa with spread spectrum is best for the city that will have a high density, and this is because we will not have so many antennas to select the IoT device. It's more or less like this, the idea. Do you think that we will not have so many antennas to have a high density in the city?
I'm not sure that this kind of I'm not sure that the I'd say antenna diversity is going to be deployed because it's going to cost much more. And one of the why LoRa is so successful right now is because it's very low cost. And I'm not sure that having multiple antenna on the device is going to be really tractable. I'm not sure about this. As I said, I'm not an expert on successive interference cancellation. What I reported is the early results in, let's say, trying to apply successive interference cancellation on LoRa signal. So right now there have been simulations, MATLAB simulations, and theoretical studies that shows promising results, but experimental studies has yet to be done.
Okay, another question, Pham. Do you know if you have some experiments doing spread spectrum in high frequency, like 60 gigahertz and terahertz?
I probably don't have enough knowledge to answer you on these questions. I'm not sure that there are really spread spectrum on this higher frequency. I don't know. Well, spread spectrum I use. I mean, could be any existing technologies. I've heard that on this high frequency that they still want to use some kind of OFDM modulation and so on. So probably that they can apply spread spectrum, but I don't want to say something wrong. So I prefer not to really answer to that question.
Okay, thank you. Nice to
thank you very much.
see you again. Okay.
Okay, thank you, Otto. Next questions.
So I thank you for the presentation. I think it is very good, very interesting about these set of protocols. So does LoRa have any consideration regarding encryptation or authentication into the wireless nodes, or that is something that is up to implement for higher layer protocols? Because one of the things that you mentioned is that LoRa focus in, instead of having multi-hop, let's say small number of devices, LoRa aims for more WAN networks that have a higher density in the nodes, and that perhaps one gateway will have to attend to a bigger number of nodes. So how does LoRa deals with this encryptation and authentication?
Yes. The physical layer has nothing to care about encryption, obviously. But you can encrypt the payload. Okay. So LoRa 1 specification, they use AES 250 bits encryption. That is quite low cost. That can be done in a few milliseconds in a very small microcontroller. So it's working fine. I haven't heard any, let's say, security issues regarding this kind of encryption. Of course, there's always a trade-off between the complexity of encryption and the cost of the encryption itself. The fact is, a lot of IoT send, let's say, temperature or pressure or whatever. Okay, so for most of these applications, the regular AES encryptions works fine. So to answer your question, so yes, higher layers such as LoRa 1, or if you want to do it yourself, it's completely feasible. Usually add AES type encryption to the payload. And they have some kind of authentication mechanism because they can have several keys, encryption keys, and then they have the message integrity check that can detect whether the sender of the message is authorized or not. Of course, this is very simple authorization mechanism, but nothing prevents you on top of that, like any other distributed system, to implement your own authentication. But this is outside of the, let's say, the LoRa. This is more, let's say, the normal distributed system authentication between network server, application servers, and so on.
Okay, thank you. Thank you very much.
Konduk, there is a question from the YouTube channel. So
Yes.
I'll read it for you, okay?
Okay.
So the question comes from Sophia, and she asks, how to prevent other gateways from listening, or better, understanding what I am transmitting? Or how can I prevent to receive unwanted transmissions?
Yes, okay. Actually, there's no way. There's no way to prevent. Because I mean, the frequency is known. So if you just put a gateway, and then you will listen, and you will be able to catch the whole transmission. So this is why LoRa 1 apply data encryption. Okay. So, I mean, to answer the question physically, there absolutely no way to prevent somebody to get your transmission. Yeah. So you have to take every precaution you want to give this transmission meaningless for the person who really catch it.
Okay, Sophia, if you want to react, I suppose the answer is very clear. So if you want to react through the chat on YouTube, don't hesitate. Okay, thank you. Any other questions from the audience?
I still have one question.
Yes.
Hi, Konduk.
Hi.
Thank you for your presentation. Thank you for your tutorial. It was very clear. Thank you very much. I just have a question about the usability of LoRa. May we say that LoRa it's gonna be the ultimate technology for outdoor IoT communication, or it's not already a ultimate technology?
It's very hard to say, because right now LoRa is definitely very successful. Okay, but the fact is, LoRa has been out there for 6 years now. But when 5G comes out, I don't know what will be the usage of 5G regarding IoT, but for sure it will change a lot in urban environment. Because if you have complete 5G infrastructures that takes into account IoT devices with low power, with very small cost for sending data, then probably people will switch from LoRa to let's say one of these 5G technologies. And then if you are in a very rural areas, maybe there's some places for LoRa, because maybe the operators don't have the coverage for 5G for IoT, so that can maintain. So it's very hard to answer this question. So probably the answer is definitely LoRa is not the ultimate technology, because right now it's successful, but with 5G in urban environment, there's some risk that it's going to move to other technologies. There will always be some kind of niche market for LoRa, because if you want to deploy something without any operators, I can see a lot of companies want to develop their own product based on private LoRa technologies, okay? Because they want to control from A to T the whole process. They build their own gateways, they build their own devices in order to propose something that is out of the box and adapted to the customer needs. Then there will always be that. And for that market, LoRa is really good, especially when we're talking about LoRa in 2.4 gigahertz band, because then the product can be deployed worldwide. Okay, you can design the same product without knowing that it can be deployed in US, can be deployed in China, deployed in India. I mean, the main problem with LoRa sub-gigahertz right now is the frequency band regulation is so complex that you cannot guarantee that when you buy a device from one country, it's going to work in another country because of the regulation. So that may change the fact. So there will always be a niche market for LoRa for very private ad hoc applications, for sure.
Thank you very much for your answer.
Thank you.
Okay, we still have time for a couple of questions. We started a little bit late, so...
May I, Marcelo?
Sure, please, go ahead, Jan.
Okay. So thank you for your presentation, Cong.
Thank you.
I have a question that is more a complement to Diogo's question. And you have just said that there will always be a niche for LoRa, right?
Yes.
So there is some competition among Sigfox, LoRa, and narrowband IoT. I would like to have your opinion about what will be the de facto standard for IoT communication in such niches.
Okay. Clearly, narrowband IoT, given the range of narrowband IoT, I mean, 1 kilometers urban and less than 10 kilometers rural, makes LoRa win. Okay, the range has nothing to compare, and also narrowband IoT, like Sigfox, is an operator technologies. So you need an operators to deploy antenna, base station, and so on. And so this is why I said, if you are in urban environment and you have all the operators deploying narrowband IoT, then probably people will use narrowband IoT. Okay, probably. But for the niche market, when you're outside, when you want to have your own system for, let's say, monitoring your agriculture, smart farming, all these applications that can be deployed without actually any operators, and maybe you want to control all your data. You don't want to upload it into any kind of operator network server or databases. Then LoRa is definitely the choice because of the how easy it is to deploy devices and gateways, and how easy it is to deploy whole system at a very low cost. So this is why I believe there will always be a niche market compared to narrowband IoT and compared to Sigfox. So Sigfox, the main problem with Sigfox is obviously not the range, okay, but it's because they definitely choose the operator approach. Okay? So they don't allow people to deploy their own Sigfox infrastructure. So did I answer your question?
Yes, thank you.
Yeah.
Any other question, guys? Don't see any questions now on the YouTube channel here on the WebEx. If you don't have any, I have a short one.
Sure.
In fact, I had a small tilt in my brain when you mentioned the numbers, because the core of the talk was about scalability.
Yes.
And at some point in time, you said, okay, you can reach like 19,000, and if I'm not wrong, something around
something
that,
like this, yes.
200, yeah, something around that. And I asked myself, of course, I don't have the answer, so that's why I'm making it to you. 19,020, is this a lot or not enough? Because we hear we have billions of IoT devices everywhere. So 19,000, I have no idea. Is it a good value or a bad value?
Well, it is a good value if we're talking about 19,000 per gateway, okay?
Yes, per gateway. That's true. That's true.
So, well, of course, it's probably a little bit provocative, okay?
Okay.
Because not all the spreading factors are orthogonal. But still, if you have 16 frequencies, you have lots of logical channels. So I think that a gateway right now, if you take a commercial gateways, having, let's say, 16 frequencies, and you have some kind of uniform distribution of the frequencies for your devices, then we are quite close to this number. So it means that people saying that, okay, there will be a scalability issues with gateway and so on, given the fact that IoT devices are not going to send much messages, then I believe that we still have room to deploy a lot of IoT devices. And I don't know, I mean, probably it's not politically correct to say, but right now, I don't see a huge deployment of IoT in the public places. Okay, a lot of IoT is deployed probably privately for companies, for some specific applications. Large-scale public IoT, like we used to write in papers, okay, billions or trillions of IoT objects on the public market or public networks. Probably too early to say that we are going to this kind of scenario.
I see. I see. Okay. I think now I believe you have to stop now because we caught up the time difference.
Okay.
So I don't think there are any other questions. We already have a few of them. And on behalf of the audience, Conduc, I'd like to thank you really a lot for the tutorial. Very informative. A lot of details that I'm sure many people did not have. So thank you again. Thank you very much. And
well, thank you. Thank you for inviting me and giving me this opportunity Maybe next time we can go to Brazil.
Yes, yes. These guys will invite you. They'll send you a flight ticket. No problem. Diogo will take care of that.
Okay.
So just before we quit today, so Diogo, correct me if I'm wrong. So tomorrow, for those who are following the conference on the YouTube channel, just use the same channel with a different link that I just sent on the chat. So see you guys tomorrow. Thank you again, Conduc.
Okay.
All
Thank
guys
you very
have
much.
a nice evening. Thank you very much. And Diogo, if you have a few last words to say, we are good for the tutorial session that we stop now.
Thank you everyone for watching this video, this presentation on YouTube, also in WebEx, and tomorrow we will start at 10 past 8 at Brazilian time. Thank you very much. Thank you for the presenters also. Thank you.